There's a force in the universe that makes certain things impossible. It's why you can't unscramble an egg. It's why you can't unbreak a glass. It's the reason a hot cup of coffee always goes cold, but a cold cup never spontaneously heats up on its own. Now, this isn't because of some complicated rule you memorized in school, like gravity or electromagnetism. It's because of probability. This force is a fundamental law of nature, a silent conductor guiding the flow of events from the beginning of time to its very end. It is the universe's hidden clock, ticking relentlessly forward. And once you see it, you'll see it everywhere, governing everything. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Think about it. Why does your room, if you leave it alone, always get messy? Why does ice always melt in a warm drink, but you never see a drink spontaneously create ice cubes? And here's the biggest question of all. Why do you remember yesterday, but have no memory of tomorrow? These aren't unrelated puzzles. They are all just different faces of the same deep principle. A principle that defines the very direction of time itself. This is the story of entropy. And it doesn't just reveal the secret of why time moves forward, but the ultimate fate of everything in the universe. The misconception and the promise. Now, you've probably heard a simple definition for entropy. Someone likely told you that entropy is just a measure of disorder or chaos. A neat room is orderly, a messy room is disorderly, so the messy room has higher entropy. Simple, right? Well, while that's a common starting point, that definition is deeply misleading. It's an analogy that hides the beautiful, simple truth of what entropy really is. The idea that the universe is just doomed to become a chaotic mess? That's not the whole story. The problem with using disorder is that it's subjective. It's a human idea. Is a sandcastle more ordered than a pile of sand? To us, sure. But physics needs something more concrete. For decades, this oversimplification has made one of the most important concepts in the universe feel confusing and abstract. So today, we're going to fix that. To really understand the universe's clock, we need to toss out the fuzzy idea of disorder and replace it with something you already get: probability. The secret to entropy isn't chaos, it's just a numbers game. It's about counting. And by the end of this, you won't just understand entropy. You'll understand why the second law of thermodynamics, the law of entropy, is maybe the single most unbreakable rule in all of nature. The core analogy, from messy rooms to probability. Let's start with a thought experiment. Forget physics for a second and imagine you have 4 coins. You toss them. What are the possible outcomes? Well, you could get all heads. There's only one way for that to happen: heads, 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 heads. That's a very specific, ordered state. You could also get all tails. Again, only one way: tails, 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 tails. Another very ordered state. But what about 3 heads and 1 tail? The tail could be the first coin, the second, the third, or the fourth. That's 4 different ways to get the same overall result. And what about 2 heads and 2 tails? If you want to work it out, you'll find there are 6 different ways for that to happen. Let's just look at the numbers. Asterisk all heads. Asterisk asterisk 1 way. Asterisk 3 heads, 1 tail. Asterisk asterisk 4 ways. Asterisk 2 heads, 2 tails. Asterisk asterisk 6 ways. Asterisk 1 head, 3 tails. Asterisk asterisk 4 ways. Asterisk all tails. Asterisk asterisk 1 way. Out of 16 possible outcomes, the most mixed state, 2 heads and 2 tails, is the most likely to happen, simply because there are more ways to get it. The highly ordered states are the least likely. You're 6 times more likely to land on 2 heads and 2 tails than you are to get all heads. This is the absolute heart of entropy. An ordered state is a low probability state because there are very few ways to arrange it. A disordered state is a high probability state because there are tons of ways to arrange it. Nature doesn't prefer disorder, it just plays the odds. And the odds, as we're about to see, get absolutely staggering. Now, let's apply this to the real world. Instead of 4 coins, imagine a box filled with just 10 gas molecules. What are the chances that all 10 molecules will, just by random motion, end up crammed into the left half of the box? The probability is tiny. It's like getting 10 heads in a row, 1 in 1024. Not impossible, but really unlikely. But what are the chances of finding them in a more disordered state, with 5 on the left and 5 on the right? Just like with our coins, there are vastly more ways for this to happen. The number of combinations is enormous compared to the single combination of all on the left. So, if you start with all the gas in one corner, a low probability state, and let it go, what happens? It spreads out, not because of some weird force called disorder, but simply because the molecules are zipping around randomly, and it is overwhelmingly more probable that they will end up in a configuration that fills the whole box. There are just more places to be. The system naturally moves from a state with few possible arrangements to a state with an astronomical number of them. This is why your room gets messy. Think of all the stuff in your room. There are only a handful of arrangements you'd call clean. But there are millions, maybe billions, of arrangements you'd call messy. As things get moved around over time, it's statistically almost guaranteed that the room will drift into one of the vastly more numerous messy states. It's not a law of decay, it's a law of large numbers. A better definition: energy and arrangements. Now we can finally define entropy properly. The idea was first worked out by the German physicist Rudolf Clausius in the 1850s, but it was the Austrian physicist Ludwig Boltzmann who gave it its true statistical meaning. His work was so important, his formula for entropy is carved on his tombstone. The formula is *S equals K log W. Now, don't let the letters scare you. The K is just a constant to make the numbers work, and the log is a math tool for handling gigantic numbers. Don't sweat them. The real star of the show here is *W. W stands for the number of microscopic arrangements of a system that all look the same from the outside. It's the number of ways you can secretly rearrange all the tiny, invisible parts of a system, the positions and speeds of all its atoms, and still have it look identical on our macroscopic level, the level of temperature and pressure we can actually measure. Let's go back to that box of gas. The macrostate is gas filling a box at a certain temperature. The microstates are the specific positions and speeds of every single molecule. There is an unimaginably vast number of different microstates, a huge W, that all look like gas filling the box. But there are very, very few microstates that look like all the gas is in the left corner. Entropy is simply a measure of W. High entropy means a high number of possible arrangements. Low entropy means a low number. This perfectly explains why heat always flows from hot to cold. A hot object is just an object where atoms are vibrating energetically. A cold object's atoms are more sluggish. When they touch, the energy from the hot object's frantic atoms gets passed to the cold object's atoms through collisions. Why does this only happen one way? Because there are vastly more ways to distribute that energy across all the atoms in both objects than there are to keep it locked up in just the hot one. The energy spreads out because the spread out state has a much higher W, a much higher number of possible arrangements. It has higher entropy. When your coffee cools down, its heat energy is spreading out into the quadrillions of air molecules in your room. The energy is moving from a concentrated, low-entropy state to a dispersed, high-entropy state. For the reverse to happen, for all those air molecules to randomly decide to give their energy back to the coffee to heat it up, is not technically impossible. But the odds are so astronomically low that you would have to wait longer than the entire age of the universe to see it happen. It is, for all intents and purposes, impossible. And this brings us to the most profound consequence of this simple law of probability. The aha moment. Entropy as the arrow of time. The basic laws of physics, like gravity or electromagnetism, don't care about time. They work perfectly forwards or backwards. A video of two billiard balls colliding looks totally normal if you play it in reverse. But the real world obviously has a direction. We see eggs scramble, but never unscramble. We see buildings crumble, but never assemble themselves from dust. We remember the past, but we can't remember the future. So, why is there an arrow of time? The answer is the second law of thermodynamics. The second law states that in an isolated system, total entropy will always increase, or at best, stay the same. It never, ever goes down. This isn't a force, like gravity. It's a statistical certainty. Because there are always more ways to be in a high entropy state than a low entropy one. That's the direction things naturally move. The universe, as a whole, is simply moving from a less probable state to a more probable one. This is the arrow of time. The reason time only seems to move forward is that the universe is on a one-way street of increasing entropy. The past, by definition, is the direction of lower entropy. The future is the direction of higher entropy. You can't unscramble an egg because that would mean moving from a high probability scrambled state to an extremely low probability unscrambled state. It would violate the second law. This leads to an incredible question. If entropy always increases, it means the universe must have started in a state of ridiculously low entropy. And it did. The state of the universe just after the Big Bang, about 13.8 billion years ago, was the lowest entropy state it has ever been in. It was an unbelievably hot, dense, and uniform soup of energy. Now, that might sound disordered, but from a gravitational point of view, it was exquisitely ordered. Gravity wants to pull things together. A smooth, uniform distribution of matter is a very low probability state for a system run by gravity. The most probable, high entropy state is for everything to be clumped together into black holes. The low entropy beginning of the universe is like starting a game with all the coins showing heads. It's a special, highly ordered condition. And from that moment on, the cosmic clock started ticking. The story of our universe is the story of it moving away from that initial, improbable state, and steadily exploring the vastly more numerous high-entropy states available to it. The grand scale, the ultimate fate of the universe. So, where does this arrow of time point? If we follow this relentless increase in entropy to its ultimate conclusion, we get to a scenario called the heat death of the universe. It's the final chapter in the cosmic story, and it's dictated by the second law. Let's take a journey into the far, far future. The stelliferous era, the age of stars, our current era, asterisk. Right now, we live in the glorious, star-filled youth of the universe. Every star is a temporary pocket of low entropy, fusing hydrogen and releasing massive amounts of low entropy energy. Sunlight, out into cold, empty space. That energy spreads out, becoming higher entropy heat. This flow from the sun's low entropy state to the universe's high entropy state is what powers everything on Earth, including life itself. But this era is just a phase. In about 5 billion years, our sun will die. Over trillions of years, the lights will go out all across the cosmos. By around 100 trillion years from now, star formation will have ended, and the last of the great stars will have faded away. The stelliferous era will be over. The degenerate era, a universe of remnants, 100 trillion to 10 to the power of 40 years, asterisk. The universe will now be a vast, dark, and cold place, populated only by the corpses of stars, black dwarfs, neutron stars, and black holes. But entropy's work isn't done. Some theories predict that over unimaginable timescales, protons themselves, The building blocks of matter are unstable and will decay. While this has never been observed, if it's true, then every dead star, every frozen planet, every last rock will slowly dissolve into a sea of radiation. The only things left to resist this decay would be black holes. The black hole era. The last beacons, 10 to the power of 40 to 10 to the power of 100 years, asterisk. Imagine a timescale so vast it makes the current age of the universe feel like a split second. In this future, the only organized matter left will be colossal black holes, orbiting silently in the dark. They are the final fortresses of order. But even they are not eternal. Thanks to Stephen Hawking, we know that black holes slowly evaporate by emitting a faint glow of particles called Hawking radiation. A supermassive black hole might take up to 10 to the power of 100 years to disappear, but eventually, even the largest among them will hiss away into nothing. The dark era. The end of time, beyond 10 to the power of 100 years, asterisk. After the last black hole has evaporated, the universe will finally approach its ultimate state, maximum entropy. It will be a cold, dark, and featureless void, expanding forever, filled with an impossibly thin, uniform soup of particles at a temperature just barely above absolute zero. This is the heat death of the universe. It's not hot, it's the death of heat transfer. Because everything is the same temperature, nothing can happen. No work can be done. No complexity can form. The universe will have reached its most probable state. In this final equilibrium, the arrow of time itself may cease to have meaning. If time's flow is a product of entropy's increase, what happens when entropy can't increase any further? The clock finally stops ticking. There is no more change. There is only being. An eternal, silent, and unchanging darkness. So, is that a depressing thought? A universe just winding down into an empty, cold nothingness? Maybe that's the wrong way to see it. The story of entropy isn't just about decay, it's the very engine of creation. The second law isn't some cosmic villain. It's the fundamental driver of change. Without the relentless push toward higher entropy, the energy of the Big Bang would have stayed locked up. Stars never would have ignited. Heat never would have flowed. The chemistry needed for planets and life would have been impossible. We exist, right now, in this brief, brilliant moment, not in spite of entropy, but because of it. We are temporary eddies of breathtaking complexity in the great, forward-flowing river of time. We are islands of order, built from stardust and powered by the light of a nearby star. All while the universe continues its grand march towards its final, most probable state. The same law that makes your coffee go cold is the law that allows for the existence of coffee, and cups, and you. It's the source of all the richness and complexity we see. So, entropy isn't just a clock counting down to the end. It's the author of the entire cosmic story. And living in the era of stars means we get to be part of the most interesting chapter ever written. If this journey through time and probability sparked something in you, share your thoughts below. What does the ultimate fate of the universe make you feel? Awe? Sadness? A new perspective? And if you want to explore more of the universe's biggest questions, be sure to subscribe for more journeys into the cosmos. The universe has a one-way ticket to total chaos. From the moment we are born, we are part of a quiet, one-way journey. Every cell, every thought, is a fleeting, ordered structure in a universe that seems to overwhelmingly favor something else. Every star in the night sky, every galaxy spinning in the dark, is on the exact same path. This is not a theory or a philosophical stance, but something woven into the fabric of reality, as certain as gravity. It's the same invisible process that guides a sandcastle, built with care, as it's slowly taken by the wind and tide, grain by falling grain, until it's just a mound, indistinguishable from the rest of the beach. It's the principle that ensures a hot cup of coffee will always, without fail, cool to match the room it's in, its useful heat lost to the air around it. It is the reason a tidy space, left to itself, will always drift towards messiness. This quiet, unstoppable universal tendency has a name: entropy. And understanding it does more than explain why coffee gets cold. It reveals something about the nature of time itself, the origin of life, and the ultimate, unchangeable fate of everything that exists. We are all passengers on a cosmic journey, and it only seems to travel in one direction, from a state of perfect order toward absolute, total chaos. The cosmic rulebook. So, what is this force called entropy? In simple terms, it's often called a measure of disorder or randomness. But a more precise way to think about it is as a measure of probability. Nature, it turns out, is a gambler. And it always bets on the most likely outcome. Imagine a box with 1,000 gas molecules inside. For a moment, let's say all 1,000 are huddled together in one tiny corner. This is a state of very low entropy. It is highly ordered, specific, and incredibly unlikely. There is only one way for all the molecules to be in that one corner. Now, what happens the instant we let them move freely? They will, with near certainty, spread out to fill the whole box. They become disorganized, randomly distributed. This is a state of high entropy. Why does this happen? It's not because of some mysterious force pushing them apart. It's just statistics. The number of ways those 1,000 molecules can be arranged in that one tiny corner is, for all practical purposes, 1. But the number of ways they can be scattered randomly throughout the box is an astronomical number, so large it dwarfs our ability to imagine it. The universe doesn't prefer chaos. It's just that there are infinitely more ways to be chaotic than there are to be ordered. A system naturally moves towards higher entropy simply because that state is overwhelmingly more probable. Think of a new deck of cards, perfectly ordered. This is a low entropy state. There is only one way for it to be perfect. Now, give it a single shuffle. The chances of it returning to that perfect order are minuscule. Shuffle it 100 times, and the chances become functionally zero. You will always end up with a random, high-entropy sequence. There are billions of ways for a deck to be disordered, but only one way for it to be perfectly ordered. The universe is shuffling itself on a cosmic scale, every single moment. This fundamental observation is captured in one of the most powerful laws in science, the Second Law of Thermodynamics. It states that in any isolated system, one that doesn't exchange energy with its surroundings, the total disorder, the total entropy, will always increase or stay the same. It can never decrease. This is the law behind why so many processes in our lives are irreversible. Imagine dropping a ceramic mug. It shatters into 100 pieces. This is the second law in action. The mug has moved from a state of low entropy, a single, ordered object, to high entropy, scattered shards. The energy neatly contained in its structure has been chaotically dispersed as sound, heat, and the motion of the pieces. Now, have you ever seen the reverse? Have you ever witnessed the shards on the floor begin to tremble and fly back together, reforming into a perfect mug as the spilled coffee leaps back inside? Of course not. It feels absurd even to consider. And yet, according to the fundamental laws of motion, it's technically possible. A movie of two atoms bouncing off each other looks just as valid played forwards as it does backward. So why doesn't the mug reassemble itself? Again, it comes down to probability. For the mug to unshatter, every single one of the trillions of atoms in those shards would have to move with the exact right velocity, in the exact right direction, at the exact right time. The odds of this happening are so small that you would have to wait a length of time that makes the age of the universe seem like the blink of an eye. It is statistically impossible. The universe permits mugs to break, but it forbids them from unbreaking. This isn't a suggestion, it is the law. And this law dictates the flow of our reality. The arrow of time. This quiet, one-way progression from order to disorder does something extraordinary. It creates the very concept of forward. It gives time its direction. This is the arrow of time. The term was coined in 1927 by the astrophysicist Arthur Eddington, who realized the second law of thermodynamics is unique. While most laws of physics are time-symmetric, the second law is directional. It is the only physical law that seems to distinguish between the past and the future. Think about your own experience. How do you know yesterday was the past and tomorrow is the future? The most fundamental answer is your memory. You remember yesterday. You do not remember tomorrow. Why? Because forming a memory in your brain is itself a process that increases the total entropy of the universe. To record information, your brain consumes ordered energy from food, and in the process of thinking and forming connections, it releases disordered waste heat. A memory is an ordered structure of information, but the cost of creating it is a net increase in the universe's total chaos. You can only create memories of events that have already happened. The arrow of time we perceive in our minds is tied directly to the thermodynamic arrow of time. The physicist Stephen Hawking identified 3 distinct arrows of time that, in our universe, all point in the same direction. There's the thermodynamic arrow, the direction of increasing entropy. Second, there's the psychological arrow, our subjective experience of time passing. And third, there's the cosmological arrow of time, the direction in which the universe is expanding. In our universe, these 3 arrows are aligned. This alignment is not a coincidence, they are deeply interconnected. Even life itself seems, at first glance, to be a violation of the second law. A single seed grows into a complex tree. A fertilized egg develops into a thinking, breathing human. These are processes of incredible ordering. So, is life a loophole? A rebellion against chaos? Not at all. Life is a temporary, local pocket of order, purchased at the cost of creating even more disorder in its environment. To maintain your complex, low-entropy structure, you must constantly consume ordered energy from food. Your body then breaks down its complex molecules, releasing large amounts of disordered energy as waste heat. The Earth itself is not an isolated system. It is bathed in a stream of low-entropy sunlight. Life captures this ordered energy. Plants use it. Animals eat the plants. The entire food chain is a cascade of energy transfer. And at every step, the vast majority of that energy is radiated back into space as disordered, high-entropy heat. So, while a tree creates local order, the total entropy of the Sun-Earth space system increases dramatically. Life doesn't fight the second law. It is a magnificent and complex vehicle for fulfilling it. It exists because entropy is increasing, not in spite of it. Life exploits the flow of energy from order to disorder, just as a water wheel exploits the flow of a river from a higher place to a lower one. Without that flow, the wheel would never turn. Without increasing entropy, life would never have begun. The cosmic story. If the arrow of time is defined by the increase of entropy, it raises a profound question. If everything is constantly getting more disordered, what does that imply about the beginning? It implies that the universe must have started in a state of almost unimaginable order. A state of incredibly low entropy. And when we look back 13.8 billion years to the Big Bang, that is what we find. But it's a form of order that is deeply counterintuitive. We tend to think of the Big Bang as a chaotic explosion, but in a thermodynamic sense, it was the opposite. The early universe was a hot, dense, incredibly smooth soup of particles and energy. And a smooth, uniform state, when gravity is the dominant force, is a state of profoundly low entropy. Think of it this way: a perfectly smooth, flat sandbox is an ordered, low-entropy state. Over time, disturbances create peaks and valleys. Gravity pulls sand into clumps. The landscape becomes more complex, but the overall state is more disordered. The initial uniformity of the Big Bang was like that perfectly smooth sandbox. There were no galaxies, no stars, no black holes. This was the universe's most ordered moment. This past hypothesis, that the universe began in this special state, is the ultimate anchor for the arrow of time. Why the universe began this way is one of the deepest mysteries in physics. We don't have a complete answer. But we know that because it started this way, the cosmic clock started ticking. The universe had an immense capacity for its entropy to increase. And so, its grand story began. In the beginning, as the universe expanded and cooled, gravity began to act. Over millions of years, it gathered the primordial gas into vast clouds, which then collapsed to form the first stars and galaxies. This seems like a decrease in entropy. A diffuse cloud becomes a dense star. But this is only part of the picture. The process of gravitational collapse releases an enormous amount of energy. When a star ignites nuclear fusion, it begins its main job, acting as a colossal entropy factory. A star is a furnace that takes ordered fuel, like hydrogen, and fuses it into other elements. But in doing so, it unleashes a torrent of disordered, high-entropy radiation as heat and light that floods out into the cold universe. The small decrease in entropy from building a star is utterly dwarfed by the monumental increase in entropy from the radiation it spews out. Galaxies are beautiful islands of order, but they are powered by engines of chaos, each one diligently working to increase the total disorder of the cosmos. We are currently living in the stelliferous era, the age of stars. It's a glorious, dynamic time. But it is a fleeting phase. The fuel is finite. The march of entropy is relentless. And as we follow the arrow of time into the deep future, the lights will, one by one, begin to go out. The ultimate fate. If we follow the arrow of time forward, not just for billions of years, but for trillions, the universe we know will become unrecognizable. The relentless increase of entropy dictates a future that is slow, cold, and profoundly lonely. This fate is often called the heat death of the universe. It is not a sudden event, but a gradual descent into equilibrium. The first stage is the end of the age of stars. In about 100 trillion years, star formation will cease. The universe's expansion, which for a long time we believed was accelerating due to dark energy, is itself a subject of ongoing discovery. While the 1998 discovery of this acceleration was a landmark, our picture of the cosmos is always being refined. Some recent studies, for instance, suggest this acceleration may have already started to slow, introducing a new layer of uncertainty into a story we thought we were beginning to understand. Regardless of the precise rate, the universe will become a realm of dying embers. Welcome to the degenerate era. For a timescale that is almost impossible to grasp, from 100 trillion years to perhaps 10 to the power of 40 years, the universe will be populated by stellar corpses, black dwarfs, neutron stars, and wandering planets. Galaxies will dissolve. Over these vast timescales, some theories predict that protons themselves will decay, and all remaining matter will slowly evaporate into a thin bath of radiation. The only things left with any real structure will be the black holes. This ushers in the black hole era. From 10 to the power of 40 to 10 to the power of 100 years, black holes will be the last organized objects. But even they are not eternal. Through a process known as Hawking radiation, they slowly lose mass. It's an incredibly slow process. A supermassive black hole might take 10 to the power of 100 years to evaporate. But the second law is patient. Entropy must increase. One by one, even the black holes will radiate away their mass until they vanish. And with the death of the last black hole, the universe enters its final stage, the dark era. What's left is a universe that has reached a state of maximum entropy. It will be a vast, cold void, filled with a diffuse sea of photons and particles, infinitesimally close to absolute zero. It will be a state of perfect and final thermodynamic equilibrium. Nothing happens because there is no usable energy left. Time itself, which is defined by change, loses all meaning. It is the end of the cosmic story. total chaos, which in the end, looks like perfect, featureless peace. Our understanding of this ultimate fate is tied to our understanding of forces like dark energy, which makes up about 68% of the universe, and as that understanding evolves, so too will the details of this distant future. This vision of the future is both quiet and profound. It places our brief, vibrant existence in a staggering cosmic context. If this kind of calm exploration helps you unwind, consider liking the video and subscribing to the channel. And I'd genuinely love to read your thoughts in the comments. What does this ultimate fate make you feel? Awe? Dread? Or something else entirely? The twist. It's easy to look at this quiet march towards an empty void and see it as a depressing conclusion. But there is another way to look at this story. There is a profound and beautiful twist. The very process of decay that leads to this desolate end is the same process that allows for our existence in the first place. Complexity, structure, and life are not things that exist in spite of this slide into chaos. They are temporary, beautiful phenomena that are generated by it. As the physicist Sean Carroll explains, the universe is on a journey from a very simple, low-entropy state, the hot, smooth Big Bang, to a very simple, high-entropy state, the cold, empty heat death. It goes from simple to simple, but the journey in between is where all the magic happens. It's in the messy, intermediate phase, as entropy is actively increasing, that there is room for complexity to arise. Think of a bottle of perfume in a sealed room. When the perfume is in the bottle, the system is simple and low entropy. When you open it and wait an eternity, the molecules will be perfectly, evenly distributed. That final state is also very simple, but it's high entropy. The interesting part is the journey. Just after you open the bottle, you get swirls and eddies, intricate patterns. You have regions of high and low concentration. The system is complex and dynamic. Life, galaxies, stars, you and I, we are those swirls and eddies. We are the complex, temporary patterns that form as the universe unfolds. For complexity to exist, you need an energy gradient. A flow. The sun provides a low-entropy source of energy, and the cold vacuum of space provides a high-entropy sink. This gradient is what powers everything on Earth. It drives the weather, the water cycles, and the intricate chemical reactions we call life. If the universe were already in a state of maximum entropy, there would be no energy gradients. No flow, no change, and therefore, no possibility for complex structures like us to form. We are not a bug in the system, we are a feature of its decay. We are the universe's way of getting from order to disorder in the most interesting way possible. So, the next time you watch a mug shatter, or feel the warmth leave a cup of coffee, you are witnessing a miniature echo of the universe's grand story. You are seeing the arrow of time made manifest. That irreversible process is the same law that set the cosmos in motion 13.8 billion years ago. It's the law that allowed gravity to sculpt the galaxies, that ignited the stars, and that drives every chemical reaction in your body that allows you to be here, thinking about it all. Our existence is a quiet, temporary arrangement of order, made possible only by the universe's slide towards something else. We are intricate sandcastles built on the shore of a cosmic ocean, destined to be washed away. But the fact that we can exist at all, that we can observe and understand the universe, is a quiet miracle born from this cosmic process. We are the temporary, complex beauty that arises as the universe falls apart. And knowing this, knowing our place in this grand, indifferent, and yet magnificent story, doesn't diminish our lives. It makes every fleeting, ordered moment infinitely more precious. The universal law that traps you in time. We experience time as a quiet constant, a flow that moves only forward. It feels fundamental, a given. But for more than a century, physicists have held a strange truth. The most basic laws that shape our universe, the rules governing every particle, do not seem to notice the difference between the past and the future. At the smallest scales, nearly everything that happens can also happen in reverse. So why is our world so different? Why does a broken egg never reassemble, its shell leaping from the floor to become whole again? Why does a drop of ink in water never gather itself from a faint cloud back into a single, dark point? We remember the past, but the future remains unknown. It turns out there is a law that holds all of this in place. It is not a law of motion or gravity. It is a law of probability. And it is called entropy. This single idea is why time has a direction, an arrow. It is the quiet, invisible current that traps you, and me, and the entire universe in a story that is written, moment by moment, with no way to turn back. The irreversible world. Our lives are a testament to the one-way nature of time. An ice cube in a warm room always melts. You never see a pool of water gather itself into a perfect cube of ice. A building, left alone, will slowly crumble to dust over centuries. It will not rise from that dust to become a pristine structure again. This is the fabric of our world. We are born, we grow older, and we never grow younger. This forward movement gives life a sense of cause and effect, of beginnings and endings. The past is the collection of things that have happened. It is fixed. The future is the space of possibility. It is unwritten. And yet, the physics beneath this reality tells a different story. The laws of motion from Newton, of electromagnetism from Maxwell, even Einstein's equations for relativity, they are all time-symmetric. If you recorded a planet orbiting a star and played it backward, the orbit would still look perfectly real. The fundamental machinery of the universe does not seem to have a preference for forward. So where does this arrow of time, the one we feel so deeply, come from? If the microscopic rules are a two-way street, why is our world a one-way path? The answer is found not in the actions of single particles, but in the collective behavior of trillions of them. The secret is not a force, but a tendency for things to move toward a state of disorder. The universe, as a whole, is moving from order to a kind of chaos. And this quiet, one-way journey is what we perceive as the flow of time. The logic of disorder, an analogy. To understand entropy, it helps to set aside physics for a moment and think of something familiar. A deck of cards. Imagine a new deck, just opened. It is perfectly ordered. The cards are arranged by suit and then by number, from ace to king. This is a state of very specific order. There is only one way for the deck to be arranged like this. We can call this a low entropy state. It is special. Now, shuffle the deck. You mix the cards. When they settle, what are the odds they will fall back into that perfect, factory-ordered sequence? The chances are almost zero. Instead, you will have a random, jumbled sequence. Here is the quiet truth at its center. This messy state is not one specific state. There are trillions of ways for a deck of cards to be shuffled. While there is only one way for the deck to be perfectly ordered, there are nearly infinite ways for it to be disordered. This is the essence of entropy. Entropy is a measure of the number of ways a system can be arranged. A low entropy state is one that can be configured in only a few ways. A high entropy state is one that can be configured in a vast number of ways. The universe does not have a desire to be messy. It simply follows the laws of probability. Because there are vastly more ways for things to be disordered than ordered, it is overwhelmingly probable that a system will move from a state of order to a state of disorder. It is not being pushed. It is simply falling into the most likely state available. Think of a room. When it is perfectly tidy, everything is in its specific place. This is a low entropy state. There are few ways for a room to be perfectly tidy. Now, live in it for a week. Books are moved, clothes are left out, papers are scattered. The room naturally tends toward messiness. Not because of a force of chaos, but because there are a million ways for the room to be messy, and only one way for it to be perfectly tidy. A sock can be on the floor, or under the bed, or on a chair. For the room to be tidy, that sock must be in one place. To go from a messy, high-entropy state back to a tidy, low-entropy one requires effort. It requires energy. You have to intentionally place each item back in its one correct position, working against overwhelming statistical odds. The simple act of cleaning a room is a temporary, local stand against the universe's most fundamental tendency. The law of entropy. Now, we can bring this idea back to physics. Instead of cards, think of atoms. A block of ice is like the ordered deck. Its water molecules are locked in a neat, repeating crystal structure. Their positions are constrained. This is a state of low entropy. When the ice melts, the molecules break free. They can now move much more freely. The number of possible positions and speeds for each molecule has grown enormously. Because there are so many more ways for the molecules to be arranged as a disordered liquid than as an ordered crystal, the system naturally moves in that direction. The ice melts. This is the second law of thermodynamics. In an isolated system, entropy will almost certainly increase. The understanding of this came from the Austrian physicist Ludwig Boltzmann. In the late 19th century, he proposed that entropy was simply a count of the number of ways the atoms in a system could be arranged without changing what we see on a large scale. His equation, S equals K log W, is carved on his tombstone. S is entropy, and W is the number of possible arrangements. The more ways there are to arrange the parts, the higher the entropy. This statistical view explains why heat always flows from a hot object to a cold one. There are vastly more ways to distribute energy so that it is spread out evenly among all molecules than for it to remain concentrated in just one place. So, through random collisions, energy spreads out. This is the state of maximum entropy, the most probable arrangement. This is why a broken egg does not reassemble. In its whole state, the egg's atoms are in a very specific, ordered arrangement. When it shatters, the pieces can lie on the floor in trillions of different configurations. The yolk and white have gone from a contained, ordered state to a splattered one where the molecules can be in an almost infinite number of positions. To go from the single, whole egg state to the countless, broken egg states is a statistical inevitability. To reverse it would require trillions of scattered molecules to spontaneously find their way back to one of the few arrangements that make up a whole egg. The odds are so small that it would never happen in the lifetime of the universe. The second law is not absolute in the way gravity is. It is a statement of probability. There is a non-zero chance that all the air molecules in your room could rush into one corner, leaving you in a vacuum. But the number of ways the molecules can be spread out is so much larger that this event is statistically impossible. The cosmic blueprint, the arrow of time. Entropy explains why things fall apart. But how does this create the arrow of time? How does this law trap us in a one-way journey? The answer is the largest special condition of all, the beginning of the universe. The second law states that the entropy of an isolated system always increases. If we treat the universe as one vast, isolated system, then its total entropy must always be rising. This implies something profound. If entropy is always increasing, then in the past, it must have been lower. And if you go back far enough, to the very beginning, the universe must have started in a state of extraordinarily low entropy. This is one of the deepest truths of cosmology. The Big Bang, the moment our universe began 13.8 billion years ago, was not a chaotic explosion. It was a state of supreme order. All the matter and energy of the universe was packed into an incredibly hot, dense, and, most importantly, unbelievably smooth state. This smoothness is the key. While a uniform gas might seem disordered to us, in a universe governed by gravity, it is actually a state of incredibly low entropy. Gravity is an attractive force. A smooth distribution of matter is unstable and improbable. The natural, high-entropy state for a universe with gravity is for matter to be clumped together into massive objects, like black holes. So, the universe was born with its entropy turned all the way down. It started in a highly specific, improbable configuration. From that first moment, everything that has happened since, every star that formed, every galaxy that spun into being, every living thing, has been part of the universe's slow journey toward higher entropy. This is the source of the arrow of time. Time has a direction because the universe had an ordered beginning. Forward, in time, is simply the direction of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. The reason we see eggs break but not unbreak is because the universe as a whole is moving from its special past to its generic future. Every irreversible event is a small ripple in this immense cosmic current. The recorder of the past, entropy and memory. This brings us to one of the most personal consequences of entropy, our own minds. Why can we remember the past, but not the future? Think of what a memory is. It is a trace, a record of a past event stored in the connections of your brain. It is an ordered pattern of information. For a memory to form, there must be a link between an event and a specific state inside your brain. The connection to entropy is subtle but deep. You can only make a record of something if the state you are recording is more ordered than the state of your recording medium. We can record the past because the past had a lower entropy. The unbroken egg is a single, low-entropy state, distinct from the messy, high-entropy, broken egg state that follows. Our brain can form a trace of this transition. Now, try to remember the future. The future is a high-entropy state of countless possibilities. There is no single, ordered state to record. It is a statistical fog. There is nothing specific for the brain to form a connection with. The very act of forming a memory is itself a process that increases the total entropy of the universe. The chemical processes in your brain that encode a memory require energy. This generates waste heat, which dissipates into your surroundings, slightly increasing the overall disorder of the universe. You are creating a small pocket of order, the memory, at the cost of creating a greater amount of disorder elsewhere. Life itself is a process that maintains local order by increasing the entropy of its environment. Our subjective feeling that time flows forward must align with this thermodynamic arrow. Our brains are physical systems. They operate by taking in energy, processing information, and creating memories, all processes that move the universe toward higher entropy. We feel time moving forward because our minds are built to operate in that direction, recording the more ordered past as we move into the more disordered future. Our consciousness is tethered to the one-way flow of increasing entropy. This is why you remember yesterday, and not tomorrow. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The cosmic finale, the heat death of the universe. We began with a broken egg, an everyday example of entropy. We have seen how this principle dictates the flow of time and our own memories. Now, let's follow this one law to the ultimate fate of everything. The journey from the Big Bang has been a spectacular one. As the universe expanded, gravity pulled the smooth gas of the early cosmos into clumps, forming stars and galaxies. This seems like an act of creating order. It is. But this local ordering comes at an enormous cosmic price. A star is a magnificent engine for increasing entropy. It achieves its temporary, ordered structure by consuming ordered fuel, hydrogen, and releasing an immense amount of energy as heat and light into empty space. This dispersal of energy wildly increases the total entropy of the universe. The small amount of order created in the star is outweighed by the colossal disorder it sends out into the cosmos. Every shining star is a beacon, signaling the relentless march of entropy. So what happens when all the stars burn out? According to the second law, the universe must eventually reach a state of maximum entropy. This state is known as heat death. It is the logical conclusion of the arrow of time. In the far distant future, all the stars will have exhausted their fuel. The universe will become dark. The remnants, white dwarfs, neutron stars, and black holes, will cool. Even black holes are thought to slowly evaporate over unimaginable timescales, returning their energy to the universe as a faint, cold radiation. Eventually, the universe will approach a state of perfect equilibrium. Every particle will be spread out uniformly across the vast, expanding cosmos. The temperature everywhere will be just above absolute zero. There will be no hot spots and no cold spots. No energy gradients. In a universe without energy gradients, nothing can happen. Life, thought, computation, all require energy flow. In a state of heat death, the universe becomes a stagnant, unchanging sea. Time, which is defined by the increase of entropy, will lose its meaning. When entropy can increase no further, the arrow of time dissolves. This is the ultimate trap of entropy. It not only forbids us from rewinding our lives but dictates that the universe itself has a finite story, a one-way journey from an ordered beginning to a cold, disordered end. From a simple glass breaking to the fading of the last star, a single principle governs the story of our universe: entropy. It is why the past is fixed and the future is open. It is why we have memories and not premonitions. It is the silent author of cause and effect. We began with a simple wish to turn back the clock. We have ended at the edge of eternity. The law of entropy tells us the rewind button does not exist. The story of our lives, and of the universe, plays only forward. But there is a strange beauty in this. The fact that the universe began in such a special, ordered state is what allows for all the complexity we see. It allows for galaxies, stars, and for life, which holds back the tide of disorder to create pockets of breathtaking structure. Every action you take, every thought you have, is a small, intricate dance with this fundamental law. You are part of this grand, cosmic story of unwinding. So, the next time you stir milk into your coffee and watch the two liquids irrevocably mix, you are watching a miniature performance of the arrow of time. You are watching the universe do the one thing it knows how to do: move forward. And in that quiet, irreversible journey, all the richness of existence unfolds. You are trapped in time, but you are also here for the ride. The cosmic glitch that makes life possible. Physics has a quiet, underlying rule: things tend to spread out. Order gives way to disorder. A neat stack of papers is carried by the wind. A hot cup of coffee slowly cools to match the temperature of the room, its useful energy bleeding away into the air. A sandcastle, built with care, is worn down by the tide until it's just a patch of wet sand. This gentle march from order to disorder has a name. It's called entropy. And according to the second law of thermodynamics, it is one of the fundamental processes of the universe. In any system left to itself, entropy can only increase. It is the law that gives time its direction, the reason we remember the past but not the future. It's why an egg can splatter but never unsplatter. But the universe itself, in its very first moments, seems to have begun in a way that goes against this tendency. It didn't start in a state of chaos, as one might expect. It didn't begin as a random, messy, high-entropy point. Instead, it began with something else entirely, a state of profound and unlikely order that scientists still work to fully understand. Our universe was born in a condition of extraordinarily low entropy. This is the story of that beginning. It is the story of an initial state so orderly and so statistically improbable that it makes everything that followed possible. And it's the quiet reason you are here, able to wonder about it at all. The stakes: a universe without the glitch. To understand why this initial order was so important, we can try a thought experiment. Let's imagine a universe that didn't have this feature. A universe that began in a state of high entropy, the state of maximum probability. What would that universe look like? The answer, it turns out, is remarkably simple. It would look very much like nothing. A high-entropy universe would be a lukewarm, featureless, uniform space. Imagine a vast, unending fog where every point is the same temperature and density. There would be no hot spots and no cold spots. No clumps of matter and no empty voids. Without those differences, without those gradients, nothing can happen. Energy only flows when there's a temperature difference, and without that flow, no useful work can be done. A universe at maximum entropy is a universe in perfect equilibrium. It is a universe that is already finished. In such a place, gravity, the great architect of cosmic structures, would have nothing to work with. Gravity needs small imperfections, regions of slightly higher density, to begin its work. It is a patient force, but it needs a starting point. In our imaginary universe, the distribution of matter and energy would be so perfectly smooth that gravity's pull in any one direction would be cancelled out by an equal pull in every other. The consequence? No stars would ever ignite. Without the gravitational collapse of vast clouds of gas, there would be no stellar furnaces to forge heavier elements. The universe would remain a thin, uninteresting haze of hydrogen and helium. No galaxies would spin into existence. No planets would form from the dust orbiting a newborn star. No complex chemistry would ever arise. And without complex chemistry, there would be no biology, no evolution, and certainly no conscious beings to observe the quiet monotony of it all. The consequences are even deeper than that. In a universe that begins at maximum entropy, even the concept of time would lose its meaning. The arrow of time, our feeling that time flows from past to future, is tied to the second law of thermodynamics. We experience time's passage because we live in a universe moving from a more ordered state to a less ordered one. If the universe had started at the end of its story, in its most disordered state, there would be no forward. Past and future would be indistinguishable. There would be no becoming, only being. So, when we say that life is at stake, we are looking at only part of the picture. Without that initial, low-entropy state, the very fabric of reality as we know it, the existence of structure, the flow of time, the potential for complexity, would not be possible. This unusual beginning isn't just a curious detail in the story of the cosmos. It is the opening sentence, the one that allows the rest of the book to be written. It is the reason there are stars in the sky, a planet beneath your feet, and thoughts in your head. It is the quiet precondition for everything. The law of the land, the two faces of entropy. Before we travel back to the Big Bang to look at this beginning more closely, we need to understand the concept of entropy itself. It's often described simply as disorder or randomness. And while that's a good starting point, the reality is a little more subtle, especially when you introduce gravity. Let's start with what scientists call thermodynamic entropy. This is the kind you encounter in everyday life. Imagine you have a box, and you release a puff of colored smoke into one corner. At first, the smoke particles are gathered together in a relatively ordered state. That's low entropy. But after a moment, the particles spread out, mixing with the air until they are distributed evenly throughout the box. That's high entropy. This happens because there are vastly more ways for the particles to be spread out than for them to be gathered in one corner. The universe, through random motion, tends toward the most probable state. Think of a new deck of cards, arranged by suit and number. This is a state of very low entropy. It is highly ordered, and there's only one way for it to be in that perfect state. Now, shuffle the deck. The cards will quickly become jumbled. This is a high entropy state. The reason you will never shuffle a jumbled deck and find it has returned to its perfect order is a matter of statistics. There are trillions of possible jumbled arrangements, but only one perfect one. This is the core of the second law of thermodynamics. Systems tend to move towards states of higher probability, which means higher entropy. Your hot coffee cools down because the concentrated heat in your cup is a low entropy state. It's more probable for that heat to be spread out evenly with the cooler air in the room. An ice cube melts for the same reason. The rigid structure of the ice is more ordered, lower entropy, than the free-flowing molecules of liquid water. So far, uniformity seems to equal high entropy. But here, gravity introduces a quiet turn. When you introduce gravity, the definition of order and disorder flips. This is the idea of asterisk gravitational entropy. In a system dominated by gravity, a smooth, uniform distribution of matter is actually a state of incredibly low entropy. It is a state of profound order and immense potential. This is because gravity is an attractive force. It wants to pull things together. A uniform gas, spread out across space, is like a field of boulders all perfectly balanced at the top of their hills. It's an unstable, low-entropy arrangement. Given the slightest nudge, gravity will begin to pull the gas into clumps. These clumps will grow, becoming denser and hotter, collapsing into stars and galaxies. This clumpy state, which to our eyes looks more structured, is actually a asterisk higher entropy state from a gravitational perspective. There are simply more ways for matter to be arranged in clumps. A star here, a void there, than for it to be perfectly smooth. Gravity finds clumpy arrangements to be the most probable, most natural state. The ultimate end point of this process, the state of maximum possible gravitational entropy, is a black hole. So now we have two different ideas of entropy. For a gas in a box, smooth and uniform equals high entropy, disorder. For matter in the universe, smooth and uniform equals low entropy, order. This is the quiet detail that unlocks the cosmic mystery. When scientists say the early universe began in a state of low entropy, they are talking about gravitational entropy. Right after the Big Bang, the universe was an incredibly hot, dense sea of particles and radiation. And crucially, it was almost perfectly uniform. The cosmic microwave background radiation, the afterglow of the Big Bang, shows us that the temperature and density of the early universe were the same everywhere to a remarkable degree. About 1 part in 100,000. From a purely thermodynamic view, this hot, uniform soup looks like it should be at maximum entropy, like the smoke in the box. But on the cosmic scale, where gravity is the dominant force, this smoothness was the exact opposite of disorder. It was the most ordered, most special, most low-entropy state imaginable. It was a universe perfectly balanced, before the inevitable, entropy-increasing process of gravitational collapse could begin. The unusual start was that gravity was handed a perfectly smooth canvas to begin its work. The grand narrative of the glitch. With this understanding, we can now tell the 13.8 billion year story of our universe as a single, unfolding process. The slow, relentless increase of entropy, all powered by that initial, ordered state. This isn't just a story of what happened, it's the story of why anything could happen at all. Our story begins in the first fractions of a second. The observable universe was unfathomably hot and dense. And yet, it was a state of shocking, almost supernatural, order. It was gravitationally smooth. How did it get so smooth? The leading idea is a process called asterisk cosmic inflation. In the very first moments of time, a mysterious energy field is thought to have driven a period of hyper-accelerated expansion. In an infinitesimally small fraction of a second, the universe swelled in size by an astronomical factor. Think of it like taking a tiny, crumpled piece of fabric and stretching it out until it's larger than a continent. All the original wrinkles would be stretched into oblivion, leaving a surface that is incredibly flat and smooth. That's what inflation did to the fabric of space-time, ironing the universe flat. When this inflationary period ended, its energy was converted into the hot, dense soup of particles and radiation we call the Big Bang. And because inflation had done its work so perfectly, this new matter and energy was distributed with breathtaking uniformity. This was the glitch in its purest form. A universe born in a state of near-perfect gravitational order, a state of profoundly low entropy. The stage was set. For the first few 100,000 years, the universe was still too hot for this order to break. It was a glowing fog of plasma, where particles of light were constantly scattering, keeping everything mixed up. But as the universe expanded, it cooled. Around 380,000 years after the Big Bang, it became cool enough for protons and electrons to combine and form the first stable atoms. Suddenly, the fog cleared. For the first time, light could travel unimpeded across the cosmos. This is the light we see today as the cosmic microwave background. And with the fog lifted, gravity could finally get to work. That initial smoothness wasn't perfectly perfect. Inflation had also stretched tiny, quantum fluctuations to astronomical sizes, seeding the universe with minuscule variations in density. Areas that were just a tiny fraction denser than their surroundings. In a high-entropy universe, these would have meant nothing. But in our low-entropy universe, they were everything. They were the handholds for gravity. Over millions and then billions of years, gravity began its patient, relentless work. In the slightly denser regions, it pulled in more gas. As matter was pulled together, the universe became less uniform. It started to get lumpy. This was gravitational entropy increasing. The perfectly ordered, smooth state was giving way to a more disordered, clumpy one. These primordial clouds grew until their cores became so hot that a new fire was lit: nuclear fusion. The first stars blinked into existence. These stars were colossal, and they burned through their fuel in a blaze of glory before exploding as supernovae. Those explosions scattered newly forged heavier elements, carbon, oxygen, iron, into the void. Gravity gathered this enriched material into the vast, spinning structures we call galaxies. Within these galaxies, smaller clumps collapsed to form new stars, including our own Sun, some 4.6 billion years ago. Every step in this narrative is a step up the ladder of entropy. Stars themselves are magnificent entropy-producing engines. They take ordered matter, simple hydrogen, and fuse it into more complex but higher entropy arrangements, releasing vast amounts of less ordered energy as light and heat into cold, empty space. The formation of planets, like Earth, is another part of this story. The disk of dust and gas around our young sun was a relatively ordered state. Gravity, in its drive to increase entropy, pulled this material into messy clumps, which eventually formed the planets. And on at least one of these planets, the process took its most remarkable turn. The rich soup of elements from long-dead stars, combined with a constant, low-entropy energy source, the light from our sun, allowed for an explosion of chemical complexity. Over billions of years, through evolution, this led to life. Life itself is a localized pocket of astonishing order. Your body is a structure of immense complexity and low entropy. But you maintain this order by constantly consuming low-entropy energy, food, and radiating high-entropy waste, heat, back into the environment. You are a temporary eddy of order in a cosmic river that is flowing unstoppably towards disorder. Every thought you have is powered by this entropy gradient, a gift from the universe's impossibly ordered beginning. From the first flicker of inflation to the evolution of a brain capable of contemplating it all, every event has been a consequence of the universe starting in a state of low gravitational entropy. Our existence is a testament to the fact that, for some reason, the universe started not at the end, but at the very beginning of its entropic story. The evidence, quantifying the improbable. We've told the story of this beginning, but now it's time to face the sheer, quiet improbability of it all. It's one thing to say the initial state was ordered. It's another to put a number on it. The physicist and mathematician Sir Roger Penrose calculated a number that is, without exaggeration, one of the most remarkable in all of science. To understand Penrose's calculation, you first had to grasp the concept of a phase space. Imagine you want to describe the state of every particle in the universe. The phase space, is a vast, abstract space that contains every single possible arrangement of all those particles. Every point in this space represents one possible state the universe could be in. Now, if you were to pick a point in this phase space at random, you would be overwhelmingly likely to hit a point representing a generic, high-entropy state. Think back to our shuffled deck of cards. The vast majority of the phase space of card arrangements corresponds to a jumbled mess. The perfect, ordered state occupies an infinitesimally tiny region. Penrose set out to calculate just how tiny that region is for our universe. He asked, out of all the possible initial states the universe could have had, what fraction of them correspond to the smooth, low-entropy state that we actually observe? He did this by first calculating the maximum possible entropy our universe could have. A state where all matter had collapsed into one gigantic black hole. This gave him the total volume of the universe's phase space. He then calculated the volume of that space corresponding to the initial conditions of the Big Bang. The number he arrived at for the odds of our specific low entropy beginning happening by chance is 1 in 10 to the power of 10 to the power of 123. It is difficult to convey what this number means. This is not one with 123 zeros after it. The number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. Penrose's number is 10 raised to a power with 123 zeros. If you were to write a zero on every single proton and neutron in the entire universe, you would not even begin to scratch the surface of writing this number out. You would run out of universe long before you ran out of zeros. This number is a measure of the precision required for our beginning. It tells us how special our starting point had to be among the vast space of possibilities. To say this is unlikely is an understatement. From a statistical standpoint, it seems almost impossible. The universe had no obvious reason to begin in such a state. And yet, all evidence suggests that it did. This isn't a fringe calculation. It's a conclusion rooted in general relativity and thermodynamics. While some scientists might debate the exact figures or the implications of inflation, the overall conclusion is robust. The initial state of our universe was special to a degree that defies conventional explanation. We started at an astronomically low point on the universal entropy scale. The existence of this number is perhaps the most important and mysterious fact about our universe. It is the piece of evidence that tells us something profound is missing from our understanding of cosmic origins. The investigation, the usual suspects. We are faced with a cosmic mystery. We have a starting point, the Big Bang, and a crucial piece of evidence, an impossibly low entropy initial state. Scientists, acting as cosmic detectives, have proposed several ideas to try and explain this. None are universally accepted, and each comes with its own set of quiet, mind-bending implications. One idea, perhaps the simplest, is to accept this beginning as a fundamental, unexplained feature of reality. Known as the past hypothesis, it suggests that the universe began with low entropy, is simply a basic law of nature. It posits that we shouldn't ask why the past was low entropy. We should just accept that it was, because this fact is necessary to explain the arrow of time as we observe it. In this view, the low entropy beginning is a brute fact. The universe is the way it is because it started that way. To many scientists, however, this feels like giving up on finding a deeper explanation. A second idea is cosmic inflation which we discussed earlier. By stretching a tiny patch of space to astronomical size, it provides a powerful mechanism for generating the low entropy state. Inflation doesn't violate the second law. Rather, it takes whatever entropy was present before and spreads it out so thinly that the universe is effectively reset. This creates the new, hot, uniform state that serves as the low-entropy starting point for the rest of cosmic history. In this sense, inflation offers a physical mechanism to produce the special conditions. However, this just pushes the question back one step. Why did inflation happen? Where did the low entropy inflated field come from? Despite this, inflation remains one of the most widely supported ideas, as it also solves several other major cosmological puzzles. A third possibility asks a different question. What if this wasn't the only attempt? This is the core idea behind the multiverse hypothesis. One version, called eternal inflation, suggests that our Big Bang wasn't a one-time event. Instead, new bubble universes are constantly popping into existence, each with its own Big Bang. If you have an infinite number of universes, then even the most wildly improbable events become inevitable. There will be countless universes that start in a high entropy state and are instantly stillborn. And scattered among them, there will be a vanishingly small number that, by pure random chance, happen to start in a low entropy state just like ours. The reason we find ourselves in one of these rare universes is simply because we couldn't exist anywhere else. This is called the anthropic principle. We won the cosmic lottery, but we couldn't have observed ourselves losing. A final class of theories suggests our Big Bang wasn't a beginning, but a transition. These are the cyclical models. Sir Roger Penrose himself is a proponent of one such model, called conformal cyclic cosmology. The idea is that our universe will continue to expand until it reaches a heat death, a vast, cold, empty state trillions of years from now. Penrose argues that at this far future point, the universe becomes geometrically similar to the hot, dense state of the Big Bang. In a quiet, mind-bending twist, the infinitely large and cold future of one eon becomes the infinitely small and hot Big Bang of the next. In this model, the low entropy state of our Big Bang is a consequence of the maximum entropy state of a previous universe. It provides a natural mechanism for resetting the cosmic clock. Each of these ideas offers a different path out of the puzzle. The one thing they all agree on is the evidence. Our beginning was anything but random. The lingering mystery. We have traveled from the first fraction of a second of existence to the far future, all in pursuit of a single cosmic anomaly. We've seen how a fundamental tendency of physics, the increase of entropy, seems to have been set aside at the very start. This quiet glitch, this state of improbable order, is not some minor curiosity. It is the foundation upon which our entire reality is built. Without this low entropy beginning, the arrow of time would have no direction. Gravity would have had nothing to shape. The stars would never have lit up the darkness. The elements that form our planet and our bodies would never have been forged. The chain of events that led from a smooth, hot plasma to a thinking human being would have been broken before its first link was ever formed. We have looked at the leading ideas, but after all this, the mystery remains. We have clues, we have theories, but we have no final answer. It is one of the deepest and most profound puzzles in all of science. It forces us to confront the unlikeliness of our own existence. We are the products of a universe that had one chance in 10 to the 10 to the 123 to begin in a way that would allow for life, and against all odds, it did. We live inside the anomaly. So, the next time you watch a sandcastle crumble, or feel the warmth of a cooling cup of coffee, take a moment. Reflect on the fact that this simple, everyday process of things falling apart is only possible because, 13.8 billion years ago, everything started together perfectly. The story of the universe is the story of that initial perfection slowly, beautifully, and creatively unwinding. What does that mean for us, these temporary constellations of stardust who have emerged from the process? What does it say about our brief moment of consciousness in the grand, unfolding story of cosmic entropy? The universe isn't telling. And perhaps, the greatest gift of this cosmic beginning is not an answer, but the profound and unending question of why we are here to ask it at all. How every star is a doomsday machine. Look up at the night sky. Away from city lights, you see a deep blackness, marked by pinpricks of light. Each one of those lights, every star, including our own sun, is part of a slow, cosmic process. They are engines of creation. The warmth and light they release make life possible. The energy from our sun drives our planet's climate, fuels its ecosystems, and allows for our existence. For all of human history, we've seen stars as symbols of permanence and constancy. But built into their very nature, into the heart of every star, is a guarantee of an eventual, quiet end. The fire that creates is also part of a process that will one day fade. The mechanism that builds worlds is the same one that ensures the universe will, over immense timescales, grow cold and dark. This is a quiet, cosmic tension. Stars are both cradles of life and instruments of an eventual end. So, how is it that every star is part of this process? And what does its fate reveal about the fate of the universe itself? To find out, we have to journey to one of the most extreme environments in the cosmos, the heart of a star. Imagine a star like our sun, shining for billions of years. You might picture it as a kind of celestial bonfire. But what's happening inside is quieter, and in many ways, more fundamental. A star isn't burning like wood in a fire. It's using the building blocks of matter in a relentless process that powers everything we see, while quietly marking the passage of cosmic time. This process has a name: entropy. Today, we're going to explore how a star's core holds a secret to the universe's ultimate state. We'll see how it forges energy, and how that energy's slow escape reveals the one-way direction of time. The cosmic forge, building the machine. Before a star can begin its journey, it first has to be built. Our story begins not with a bang, but in the cold, dark, and seemingly empty voids between the stars. These regions are not truly empty. They are filled with vast, calm clouds of gas and dust, mostly hydrogen, the simplest element in the universe. These are stellar nurseries, the places where stars are born. For millions of years, these clouds can drift peacefully. But the universe is never completely still. A shockwave from a distant exploding star, or a gravitational nudge from a passing galaxy, can disturb this quiet. This small disturbance is all it takes for the most patient force in the cosmos to take over: gravity. Gravity pulls things together. Within the gas cloud, some regions are slightly denser than others. These denser clumps begin to pull in more material from their surroundings. As their mass grows, their gravitational pull increases, allowing them to gather even more gas and dust. It's a slow, patient accumulation. As this clump, now called a protostar, continues to collapse, something remarkable begins to happen. The particles inside are squeezed closer together. Compressing a gas heats it up. Now, imagine that on the scale of billions of tons of hydrogen gas collapsing under its own immense weight. The pressure and temperature at the center of the protostar start to climb. The core becomes a place where protons, the nuclei of hydrogen atoms, move at incredible speeds. For a long time, their positive electric charge keeps them apart. But as the temperature continues to rise, reaching millions of degrees, these protons move faster and faster. And then, a threshold is crossed. The core temperature hits about 15 million Kelvin. At this point, the protons move with such speed that they can overcome their repulsion and fuse together. This is the moment of ignition. Nuclear fusion begins. In stars like our Sun, the main process is the proton-proton chain. It's a multi-step process for turning hydrogen into helium. First, two protons fuse. One proton transforms into a neutron, releasing a positron and a particle called a neutrino. This new combination, one proton and one neutron, is a form of hydrogen called deuterium. Next, another proton collides with this deuterium nucleus, creating helium-3. This happens twice, giving us two helium-3 nuclei. Finally, these two helium-3 nuclei collide and fuse. Two protons are released, and what remains is a single, stable nucleus of helium-4. If you were to weigh the initial 4 protons and the final helium-4 nucleus, you would find that the helium-4 nucleus is about 0.7% less massive. Mass has vanished, but it has been converted into pure energy, described by Einstein's equation, E equals mc squared. The energy released from this tiny amount of lost mass is immense. In the Sun's core, this happens on an unimaginable scale. Every second, about 620 million metric tons of hydrogen are fused into 616 million metric tons of helium. That missing 4 million tons of matter is converted into a colossal amount of energy. This is the power source of the star. For stars more massive than our Sun, another process begins to play a much larger role, the CNO cycle. In these hotter, denser cores, atoms of carbon, nitrogen, and oxygen act as catalysts, helping to fuse hydrogen into helium at a much faster rate. This continuous release of energy from the core creates an enormous outward pressure, pushing against the inward pull of gravity. For most of a star's life, these two forces are in a delicate balance. Gravity tries to crush the star, and fusion pressure pushes back. This stalemate is called hydrostatic equilibrium, and it's what keeps a star stable for billions of years. The star has found its balance, but the very process that keeps it stable is also part of its eventual end. The inescapable law, the underlying process. The star is now a stable, self-regulating body. For billions of years, it will steadily convert hydrogen into helium. But there is a fundamental rule written into the fabric of the universe that it cannot escape. The energy created in the core must get out. And the way it gets out reveals the underlying process. This process is governed by one of the most fundamental concepts in physics, entropy. To understand it, let's follow a single particle of energy, a photon, born in the Sun's core. This photon begins as a high-energy gamma ray. Its goal is the surface, but its path is not direct. The core of a star is incredibly dense. The photon travels only a few millimeters before it is absorbed by an atom. That atom then re-emits the photon in a random direction. It's a journey without a straight line, often called a random walk. This takes place in the star's radiative zone. A single photon can be absorbed and re-emitted millions of times. What started as one powerful gamma ray is gradually split into thousands of lower energy photons. The journey is incredibly slow. It can take a photon anywhere from 10,000 to over 170,000 years just to cross this zone. Once the energy reaches the outer layers, the convective zone, the process changes. Here, large currents of hot plasma absorb the energy, rise toward the surface, release their heat into space, cool, and sink back down. Finally, after a journey that may have lasted for hundreds of thousands of years, the energy emerges from the surface as thousands of photons of visible light and heat. This entire process is a perfect illustration of entropy. So what is entropy? You may have heard it described as disorder, but a more useful way to think about it is as the dispersal of energy. Nature has a tendency for energy to spread out, to move from a concentrated state to a dispersed one. Imagine a drop of ink in a glass of water. Initially, the ink is concentrated, a low entropy state. But it quickly spreads out until the entire glass is a uniform, light gray. The system has reached a state of higher entropy. You will never see the reverse happen spontaneously. This is the second law of thermodynamics. In an isolated system, entropy tends to increase. Now, let's apply this to our star. The core is an incredibly concentrated, low-entropy state. The cold vacuum of space around it is a vast, high-entropy state. The second law dictates that the energy from the hot, concentrated core must flow outwards to the cold, empty space. Every photon that escapes the star's surface is a small, irreversible step towards increasing the total entropy of the universe. It carries concentrated energy away from the star and spreads it into the void, where it becomes dilute. The star, simply by shining, is an engine of entropy. It relentlessly converts ordered matter into dispersed energy. This is the underlying process. It's not a flaw, it is the star's primary function from the universe's perspective. The star's life is a constant, losing battle to maintain its own low entropy state against the second law. The very light that gives us life is a quiet signal of the universe's slow journey towards a final state of equilibrium, sometimes called the heat death of the universe. Every star is a beautiful, temporary pocket of resistance against this cosmic trend. But in resisting it locally, it accelerates it globally. The doomsday clock is ticking, one photon at a time. The two fates, the machine's final sequence. The machine cannot run forever. The fusion of hydrogen into helium relies on a finite supply of fuel. Eventually, the hydrogen in the star's core will be used up. When the fuel runs out, the final phase begins. What happens next depends on one factor: the star's mass. This property determines which of two paths the star will follow. One is a quiet, slow fade into darkness. The other is one of the most energetic events the universe has to offer. Let's first consider the fate of low-mass stars, like our own Sun. After about 10 billion years, the Sun will have converted most of the hydrogen in its core into helium. With fusion stopping in the core, the outward pressure vanishes. Gravity begins to win, and the helium core starts to collapse. This collapse causes the pressure and temperature to rise. While the core itself is no longer fusing, a shell of hydrogen just outside it becomes hot enough to ignite. This new burst of shell fusion generates even more energy. The outward pressure pushes the star's outer layers further and further out. The star begins to swell, transforming into a red giant. Its surface expands and cools, giving it a reddish color. When our Sun becomes a red giant in about 5 billion years, it will likely swell to engulf the orbits of Mercury and Venus, and possibly Earth. Meanwhile, the helium core continues to contract and heat up. When the temperature reaches about 100 million Kelvin, a new fusion process ignites. The triple alpha process, where 3 helium nuclei fuse into a carbon nucleus. In a star like the Sun, this happens in a rapid event called the helium flash. The star finds a new, temporary equilibrium, fusing helium into carbon. But this phase is short. Helium is a less efficient fuel, and it runs out much faster. Soon, the core is filled with carbon and oxygen. For a star of the Sun's mass, there is not enough pressure to heat the core to the 600 million Kelvin required to fuse carbon. The star is out of fuel options. It becomes unstable, and its outer layers are puffed out into space. These expelled layers, lit up by the hot, exposed core, form a beautiful object, a planetary nebula. What's left behind is the star's dead heart, a white dwarf. It's an incredibly dense object, with a mass comparable to the Sun squeezed into a volume the size of Earth. It no longer produces new energy. It is a hot ember that will spend trillions of years slowly radiating its leftover heat into space, eventually fading into a cold, invisible black dwarf. This is the quiet end, a slow decay into darkness. Now, let's turn to the fate of high-mass stars, those born with 8 times the mass of our Sun or more. Their lives are short, and their deaths are very different. Because of their immense mass, the pressure in their cores is far greater. They burn through their fuel at a furious rate. When the hydrogen runs out, the core collapses, and the star swells into a red supergiant. But unlike a low-mass star, its core becomes hot enough to fuse helium into carbon, and then it continues. Carbon fuses into neon, neon into oxygen, and oxygen into silicon. The star's interior becomes like an onion, with concentric shells each fusing a different element, all the way down to a core of silicon fusing into iron. And there, the process comes to a sudden stop. Fusing all elements up to iron releases energy. But fusing iron nuclei consumes energy. In an instant, the furnace at the heart of the star turns off. The outward pressure vanishes. Gravity wins, completely and catastrophically. The iron core collapses in on itself in less than a second, shrinking from the size of the Earth to a ball of matter only a few dozen kilometers across. The outer layers of the star come crashing down, slam into the new, dense core, and rebound. This rebound creates a titanic shockwave that blasts outwards. This is a supernova. The explosion tears the star apart, briefly outshining its entire host galaxy. It is an event of unimaginable scale, a machine tearing itself apart. We've journeyed into the heart of a star and witnessed its two possible fates. Both are driven by the same inescapable laws. It's a profound idea, connecting the lights in our sky to the ultimate state of the universe. If you find these grand narratives of the cosmos as fascinating as we do, consider subscribing and joining us as we continue to explore these questions. And let us know in the comments, does the idea of the universe having a final, quiet end change how you view our place within it? Cosmic aftermath and conclusion. Legacy of the machine. The star has reached the end of its life. For a low-mass star, it has left behind a glowing nebula and a cooling ember. For a high-mass star, it has ended in a cataclysm. It seems like the end of the story. But it's not the end. Because from the ashes of this destruction comes the possibility of creation. The supernova is not just an explosion, it's a forge. The core of the massive star created elements up to iron. But all the elements in the universe heavier than iron, the copper, the silver, the gold, the uranium, are created in the unimaginable energies of a supernova explosion in a process called rapid neutron capture. The supernova then scatters these newly forged elements far and wide across the galaxy. This cosmic dust enriches the vast clouds of hydrogen from which the next generation of stars will be born, and the planets that will orbit them. The planetary nebulae of low-mass stars do the same, seeding space with lighter elements like carbon and oxygen. The death of one star provides the raw material for the birth of others. Now, bring this story home. Look at your hand. Consider the calcium in your bones, the iron in your blood, the oxygen you are breathing. Every one of those atoms, every atom in your body heavier than hydrogen and helium, was created inside the heart of a massive star that lived and died billions of years ago. That star, in its final moments, scattered those atoms across space. Over billions of years, gravity gathered that stardust into a new cloud, which collapsed to form our Sun and the planets, including Earth. We are, in the most literal sense, made of stardust. Our existence is owed to these stellar processes. And so we arrive at a final, profound conclusion. We began with attention. The star as both a creator and as part of an inevitable end. We now see that these two identities are not just connected, they are the same. The star is an engine of entropy, pushing the universe towards an ultimate heat death, a final state of cold, dark uniformity. But in the process of playing its part in this cosmic endgame, the star creates pockets of complexity. It forges the elements necessary for planets and for life. The very mechanism that guides the universe toward a quiet end is the same mechanism that allows the universe to be alive today. The process that ensures the end of everything is the same process that made our beginning possible. Life is not a defiance of the second law of thermodynamics, but a temporary and beautiful consequence of it. So the next time you look up at the night sky, at the countless stars scattered across the darkness, remember what you are seeing. You are not just looking at distant lights. You are looking at your cosmic ancestors. You are looking at the engines that built the world. And you are looking at the quiet clocks, each one counting down, second by second, to an ultimate, inevitable end. They are the creators and the destroyers, the beginning and the end, all in one. They are the doomsday machines that gave us life. Why you have to eat to stop yourself from disintegrating. Every moment, your body is engaged in a quiet, constant effort. A fundamental principle of the universe dictates a path towards simplicity and disorganization. Yet, you exist as a structure of almost unimaginable complexity. The process that allows you to persist against this universal tendency is your last meal. This is a journey into how food provides the necessary order to maintain your own existence. The cosmic principle. Before we can understand this process, we must first understand the context in which it operates. This context is not a force of malice, but a fundamental principle of reality known as the Second Law of Thermodynamics. Its core concept is simple. In any closed system, things tend to move from a state of order to a state of disorder. Consider a sandcastle built on a beach. It is a structure of significant order, created from scattered, disorganized grains of sand. But over time, the wind and the tide act upon it. The castle erodes, its intricate forms returning to a simple, disorganized heap. The order that was imposed upon it is lost. Or think of a cup of hot coffee left on a table. The heat is a concentration of energy, an orderly collection of fast-moving molecules. Left to itself, this heat does not become more concentrated. It dissipates into the cooler, more disorganized air of the room. The energy spreads out, becoming more random. This progression from order to disorder is measured as an increase in entropy. Entropy is, in essence, a measurement of randomness. The second law states that the total entropy of an isolated system will always increase over time. A tidy room tends towards messiness. A star burns out and dissipates. A mountain erodes to dust. This is the default trajectory of the universe. Now, consider your own hand. Think of the intricate network of skin, bone, muscle, and nerves. Deeper still are the trillions of cells, each a complex city of microscopic machinery, all operating in synchrony. Even deeper are the molecules that form these cells. DNA, a spiraling library of information. Proteins, folded into precise shapes that function like microscopic robots. You are among the most highly ordered systems known to exist. You are a sandcastle of staggering complexity. According to a fundamental rule of the universe, such a high degree of order is improbable and requires constant maintenance to persist. Every random molecular motion, every moment that passes, is like a wave washing against this structure, tending to break it down and return its highly ordered atoms to a more chaotic state. This is the physical reality we inhabit. The universe tends towards disorganization, and the fact that life has not only emerged but continues to exist is a remarkable phenomenon. This is the cosmic principle, a constant, underlying tendency toward disintegration. The biological counterpoint. In the context of this universal principle, your body is a counterpoint. It is a fortress of order, a system that actively maintains its own complex structure. The scale of its organization is difficult to fully comprehend. Your body is composed of an estimated 37 trillion cells. This is not just a homogeneous mass. There are over 200 distinct cell types, each specialized for a particular function. Nerve cells form a communication network more complex than the global internet. Muscle cells contract in unison to produce movement. Retinal cells can detect a single photon of light. Immune cells patrol the body, identifying and removing foreign invaders. Within each of these 37 trillion cells, thousands of chemical reactions occur every second. Proteins are assembled, signals are transmitted, and repairs are made. Your DNA is being read and replicated with remarkable fidelity. All of this happens without conscious direction. Your heart beats approximately 100,000 times a day, circulating blood through nearly 100,000 kilometers of blood vessels. Your lungs take over 20,000 breaths, extracting the oxygen required for these processes. This is not a static structure, but a dynamic, self-repairing system. Every day, your body produces hundreds of billions of new cells to replace old ones. Your skin replaces itself over a matter of weeks. Your skeleton is completely remodeled over the course of about a decade. You are not the same physical entity you were 10 years ago. You are a flowing river of matter, constantly rebuilding yourself to maintain your form. This constant activity of building, repairing, and maintaining is the essence of life's response to entropy. Entropy tends to break things down. Your body does the opposite. It builds complex molecules from simpler ones, assembling them into cells, tissues, and ultimately, you. This process requires a continuous and significant input of energy. Without this constant energy supply, the building and repair cease. The relentless force of entropy then becomes the dominant process. The ordered structures begin to break down. The complex molecules unravel. This is disintegration, not a dramatic event, but a quiet surrender to the second law. So how does the body acquire the energy for this perpetual maintenance? It does so by finding and consuming pockets of order from the external world. It ingests things that are themselves low in entropy, systematically dismantles them, and uses their stored order to maintain its own. This is the role of your last meal. That food is not just sustenance. It is a delivery of order, the raw material for the continuation of your own complexity. The nature of biological energy. To understand how a meal can counteract this cosmic tendency, we must clarify what energy means in a biological context. It is synonymous with order. Consider a piece of coal versus a puff of smoke. The coal is a highly structured, dense package of carbon molecules, a low-entropy object. The smoke is a disorganized, scattered cloud of particles, a high-entropy object. The usable energy is stored in the asterisk structure of the coal. Burning it releases that order as chaotic heat and light, increasing the total entropy of the surrounding universe. Food functions in a similar way. An apple, for instance, is a marvel of low-entropy organization. It is a structured package of complex sugar molecules, which a tree built using energy from the sun. The tree took simple, high-entropy molecules like carbon dioxide and water and, through photosynthesis, used the ordered energy of sunlight to forge them into complex, low-entropy sugars. The apple is, in effect, a battery charged with order captured from the sun. When you eat that apple, you are consuming its stored order. Nutrients are substances essential for growth and maintenance, providing the materials and energy the body requires. If we do not acquire the right nutrients, our metabolic processes cannot function correctly, and our health declines. This brings us to a key insight about life. Living things do not violate the second law of thermodynamics. Instead, they are masters of exploiting it. A living organism is what is known as an open system, constantly exchanging matter and energy with its environment. Life maintains its own internal, local island of order by creating an even larger amount of disorder in the universe around it. Consider a refrigerator. Its purpose is to create a low-entropy environment, a cold, ordered space. It does this by using a pump to transfer heat from its interior to the exterior. The back of a refrigerator is warm. It is dumping disordered energy into the kitchen. The refrigerator makes the room slightly more chaotic to keep its own interior ordered. The total entropy of the system, the kitchen plus the refrigerator, increases, satisfying the second law. Your body is like that refrigerator. You consume a low-entropy apple. Your body breaks down its ordered molecules and uses the energy released to build its own, even more complex structures and to power its functions. This process is not perfectly efficient. A large amount of the energy from the apple is radiated away as heat, warming the air around you. You exhale carbon dioxide and water vapor, simple, high-entropy molecules. You are a machine that takes an order, uses some of it for self-maintenance, and exports a larger amount of disorder back into the environment. Life is, in fact, one of the most effective entropy-generating processes known. The universe's journey towards randomness is accelerated by the presence of life. The fuel for this process is these packages of low-entropy chemical energy: carbohydrates, fats, and proteins. Metabolism is the collective term for the processes that convert this fuel into usable power. But before this fuel can be used by individual cells, it must be processed and delivered by the digestive system. The supply chain, a journey through the digestive system. The journey from food to cellular energy is a process of systematic deconstruction, designed to break down the ordered structures of what we eat into their fundamental components. This internal supply chain begins before the first bite. The sight or smell of food can activate the salivary glands, a preparatory step known as the cephalic phase of digestion. The first stop is the mouth, where mechanical and chemical processing begins. The teeth grind the food, increasing its surface area for the chemical processes to follow. Saliva contains enzymes, most notably salivary amylase, which immediately begins to break down complex carbohydrates into simpler sugars. Saliva also lubricates the food, forming it into a soft mass called a bolus for the next stage of its journey. Swallowing initiates peristalsis, a series of involuntary muscle contractions. The muscular tube of the esophagus propels the bolus downward toward the stomach, a system that works independently of gravity. The bolus then enters the stomach, a highly acidic environment. The stomach walls secrete hydrochloric acid, creating a pH between 1.5 and 3.5. This acid serves two main functions. It sterilizes the food, killing most harmful microorganisms, and it begins to denature proteins. Proteins are long chains of amino acids folded into specific three-dimensional shapes. The acid causes these proteins to unfold, making them accessible to the next agent the stomach deploys: pepsin. Pepsin is an enzyme that cuts the long protein chains into smaller fragments called peptides. The stomach churns this acidic slurry, now called chyme, for several hours. Once processed, the chyme is released in small amounts through the pyloric sphincter into the small intestine. This long, coiled tube is the primary site of digestion and absorption. As the acidic chyme enters the first section, the duodenum, it triggers a cascade of chemical signals. The pancreas releases a flood of digestive juices containing a variety of enzymes. Pancreatic amylase continues the breakdown of carbohydrates into simple sugars. Lipase attacks fat molecules, breaking them into fatty acids and glycerol. Proteases, such as trypsin, continue breaking down proteins and peptides into individual amino acids. This pancreatic juice also contains bicarbonate, which neutralizes the stomach acid, protecting the intestinal wall. Simultaneously, the liver produces bile, which is stored in the gallbladder. When fat enters the small intestine, bile is released. Bile acts as an emulsifier, breaking large fat globules into smaller droplets. This increases the surface area for the lipase enzymes to act upon, much like dish soap breaking up grease. At this point, the food has been reduced to its basic molecular components: simple sugars, amino acids, and fatty acids. These are the refined molecules that cells can use. The final challenge is to transport them into the bloodstream. The inner surface of the small intestine is covered in millions of tiny, finger-like projections called villi, which are themselves covered in even smaller microvilli. This structure creates a vast surface area for absorption, comparable to the size of a tennis court. Specialized cells on this surface transport the nutrient molecules into the capillaries and lymphatic vessels. Simple sugars and amino acids enter the bloodstream directly and are transported to the liver. Fatty acids take a separate route through the lymphatic system before eventually entering the bloodstream. The remaining material, mostly indigestible fiber and water, passes into the large intestine. Here, most of the water is reabsorbed, and a complex community of gut bacteria may break down some remaining fiber and synthesize certain vitamins. This entire journey is the logistical process that fuels the body's maintenance against entropy. The supply chain has delivered the fuel. Now, it must be converted into power. The power plants, cellular respiration. The fuel, primarily the simple sugar glucose, now circulates in the bloodstream. It arrives at one of the 37 trillion cells. The process of converting a sugar molecule into usable energy is called cellular respiration, and it occurs primarily within specialized organelles known as mitochondria. Imagine a single cell. The nucleus contains the DNA blueprints. Ribosomes are factories for building proteins. The mitochondria are the power plants, providing the energy for all cellular operations. A glucose molecule enters the cell's cytoplasm, where the first stage of cellular respiration, glycolysis, begins. This process is so fundamental it occurs in nearly all living organisms. In a series of 10 chemical reactions, the 6-carbon glucose molecule is split into two 3-carbon molecules of pyruvate. This initial stage yields a small net profit of 2 molecules of a universal energy carrier, adenosine triphosphate, or ATP. ATP is often called the cell's rechargeable battery. It consists of an adenosine molecule attached to 3 phosphate groups. The bond holding the third phosphate group is a high-energy bond. When the cell needs energy, it breaks this bond, releasing the energy and converting ATP to ADP. Adenosine diphosphate. A. Spent battery. Glycolysis provides a quick but small amount of energy. The vast majority of the energy remains locked in the pyruvate molecules. To access it, the pyruvate is transported into the mitochondria. A mitochondrion has 2 membranes, a smooth outer membrane and a highly folded inner membrane. These folds, called cristae, dramatically increase the surface area available for the final stages of energy production. Inside the mitochondrion, pyruvate is converted into a 2-carbon molecule called acetyl-CoA, releasing a molecule of carbon dioxide in the process. This is some of the CO2 that we exhale. Acetyl-CoA then enters the second stage, the Krebs cycle, or citric acid cycle. Here, the molecule is systematically dismantled. Its carbon atoms are released as more carbon dioxide. The primary purpose of this cycle is to harvest high-energy electrons from the fuel molecule and load them onto specialized carrier molecules, primarily NADH and FADH2. These loaded carriers proceed to the final stage, the electron transport chain, which is a series of protein complexes embedded in the folded inner mitochondrial membrane. The NADH and FADH2 molecules unload their high-energy electrons, which are then passed down the chain from one protein to the next. The energy released at each step is used to pump protons across the inner membrane, creating a powerful electrochemical gradient, a reservoir of potential energy, similar to water behind a dam. These protons can only flow back through a single channel, a molecular marvel called ATP synthase. It is a biological turbine. As protons rush through it, a part of it spins, providing the mechanical energy to reattach a phosphate group to ADP, regenerating a fully charged molecule of ATP. This final process, chemiosmosis, is incredibly efficient. From a single starting molecule of glucose, this entire pathway can produce up to 30 to 32 molecules of ATP. At the very end of the chain, the now low-energy electrons must be removed. This is the critical role of oxygen. An oxygen atom accepts the spent electrons and combines with protons to form water, a harmless byproduct. Without oxygen as the final electron acceptor, the entire system would halt. This is why breathing is essential for our survival. In every cell, every moment, this process is converting the order contained in food into the energy that powers life. It is the energy used to build, repair, and hold off the relentless tendency toward disorder. When the fuel runs out, we have observed the intricate processes of digestion and cellular respiration, all aimed at producing the ATP that maintains order. What happens when the fuel supply is interrupted? When the supply of glucose from food ceases, the body initiates a series of survival protocols. For the first 6 to 24 hours, it draws upon its emergency reserves of glycogen, a storage form of glucose in the liver and muscles. This glycogen is broken back down into glucose to maintain blood sugar levels, particularly for the energy-demanding brain. These stores are limited. After they are depleted, the body shifts to burning fat in a state known as ketosis. Fat stores are broken down into fatty acids, which most cells can use for energy. The liver also converts some fatty acids into ketone bodies, an alternative fuel the brain can use. This adaptation allows for survival for an extended period by consuming the body's largest energy reserve. This is a survival mode, however, not a sustainable state. Without incoming nutrients, non-essential processes like cell repair and replication are reduced. If the fast continues and fat reserves diminish, the body enters its most destructive phase. It begins to break down its own protein structures for fuel. Muscle tissue is broken down into amino acids, which are converted into glucose in the liver. This process, proteolysis, is the body consuming its own structure, muscles, organ tissues, even the heart, to keep the brain alive. This is an extreme form of autophagy, or self-eating, a process that is normally a healthy recycling mechanism but becomes destructive during starvation. At the cellular level, the consequences are catastrophic. Without sufficient ATP, the fundamental machinery of life stops. The ion pumps in cell membranes fail, disrupting the delicate electrochemical balance. DNA repair ceases, and errors accumulate. The synthesis of new proteins stops. The intricate, ordered city of the cell descends into chaos. Its structures begin to disintegrate. Ultimately, death from starvation is often due to heart failure, as the cardiac muscle, having been broken down for fuel, no longer has the strength to pump blood. The system of order has exhausted its resources. The second law of thermodynamics reasserts its authority. The body, no longer maintained by a constant flow of energy, returns to equilibrium with its surroundings. It cools, its complex molecules break down, and it returns to the simpler components from which it was assembled. The reason we eat is tied to the very definition of life. It is the story of maintaining a temporary, local island of order against a universal tendency toward chaos. Every meal is a delivery of organized matter, acquired from the environment to perpetuate your own intricate structure. From the systematic deconstruction in your digestive system to the molecular turbines within your mitochondria, your body is a quiet reminder of life's improbable nature. You do not defy the laws of physics. You are a product of them, a complex system that persists by processing order, creating a net increase in disorder in your surroundings to maintain your own existence. The next time you sit down for a meal, you are not just satisfying hunger. You are participating in the constant, delicate process of your own reconstruction. Why a black hole is the most disordered thing in the universe. A room can be disordered. Clothes on the floor, books piled up, a forgotten coffee mug. A physicist would call this a state of high entropy. It is chaotic, and there are many ways it could be arranged and still be considered messy. A perfectly organized room, by contrast, is a state of low entropy. Everything is in its specific place. It is ordered. It is simple. We often think of this idea, entropy, on a human scale. A tidy desk, a shuffled deck of cards. But we can scale this concept upward. To an entire galaxy, with its billions of stars, its swirling gas clouds, and its countless planetary systems. A galaxy would seem to represent a staggering amount of disorder. But this entire galaxy, with all of its chaotic motion, is a pristine and almost perfectly ordered place when compared to the quiet, unimaginable chaos held within a single black hole. That is the paradox. A black hole, an object that can be described by just three properties, its mass, its spin, and its charge, appears to be the most disordered, most chaotic thing in the entire universe. It does not seem to make sense. An object of supreme simplicity holding the title for maximum chaos. This is not just an interesting idea. It is a conclusion that sits at the heart of modern physics, a discovery that saved one of science's most fundamental laws from being broken. This is the story of a quiet contradiction, a puzzle that occupied some of the greatest minds in physics, and the final understanding that black holes are not destroyers of disorder. They are its quiet champions. And understanding why changes how we see the universe. Before we can appreciate the deep disorder of a black hole, we must first understand what disorder means in physics. The scientific term is entropy, and it is a subtle but profound concept. At its core, entropy is a measure of hidden information. It is the number of ways you can secretly rearrange the microscopic parts of a system without changing its overall macroscopic appearance. Consider the room again. If your books are arranged alphabetically, there is only one configuration for them. The entropy is low. But if you throw them on the floor, there are a vast number of ways they can be arranged and still be called a messy pile. Each of these hidden arrangements is a microstate. The overall appearance, the messy pile, is the macrostate. High entropy means there is a vast amount of hidden information about the precise state of all the small things that make up the big thing. This brings us to one of the most foundational laws of physics, the Second Law of Thermodynamics. It states that the total entropy of an isolated system can only stay the same or increase over time. It never decreases. Things naturally move from order to disorder. An egg breaks, but it does not unbreak. Ice melts in a warm room. Perfume expands to fill a space, it never gathers itself back into the bottle. This quiet, one-way progression toward increasing disorder is what gives time its arrow. The universe itself is moving from a state of lower entropy, the highly ordered conditions just after the Big Bang, to a state of higher entropy. This law was thought to be absolute. For a time, however, it seemed physicists had found a perfect exception. An object capable of committing the ultimate cosmic transgression, deleting entropy from the universe. That object was the black hole. To understand the problem, we first need to understand the object. A black hole is born from the death of a massive star. When the star runs out of fuel, the outward push of fusion stops. Gravity wins. The star's core collapses under its own weight, crushing down into an impossibly small point. If the core is massive enough, gravity becomes so strong that nothing, not even light, can escape. This point of no return is called the event horizon. It is not a surface you could touch. It is a boundary in spacetime. Once crossed, all paths lead inward to the singularity, a point of infinite density. Here, the problem begins. In the 1970s, an idea called the no-hair theorem became accepted. It stated that once a black hole forms, it loses almost all the complexity of the object that created it. A star is complex. It has a chemical composition, a magnetic field, a unique structure. When it collapses, all of that intricate information seems to be lost. According to the theorem, the final black hole can be described by just three numbers: its mass, its spin, and its charge. That is all. It holds no information about what it was made of. Black holes, in this view, are the simplest objects in the universe. They have no hair, no mess, no hidden information. They are the embodiment of low entropy. And this sets the stage for a profound puzzle. We have our law, the Second Law of Thermodynamics, which states that total entropy must always increase. And we have our object, the black hole, a supposedly simple, low-entropy thing. Imagine we take a box of hot gas. This gas has a huge amount of entropy. The atoms are in a chaotic, disordered state. Now, we throw this box of high-entropy gas into a black hole. From the outside, the gas crosses the event horizon and disappears. It is gone from the observable universe. The information about the position and velocity of every gas molecule is now hidden, inaccessible. The entropy that was in the gas appears to have been erased. The black hole grows slightly more massive. Its event horizon expands, but according to the no-hair theorem, it remains a simple object. It does not seem to have inherited the disorder of the gas it swallowed. This was the paradox. If you drop a hot cup of tea into a black hole, you seem to hide the evidence of its disorder. The entropy of the outside universe has gone down, and the black hole shows no sign of having any entropy to compensate for it. The second law of thermodynamics appears to be violated. This was not a small problem. If the second law could be broken, our understanding of time and the universe's evolution would be incomplete. Physics needed an answer. Did black holes really destroy disorder? Or was there something about them we were missing? The first clue came not from a veteran physicist, but from a graduate student at Princeton University named Jacob Bekenstein. He had a radical thought. What if the information is not destroyed? What if the black hole itself has entropy? And what if that entropy increases when something falls in? This was a difficult proposal. How could a simple object possess entropy, which is a measure of hidden complexity? Bekenstein found his answer in a discovery made by Stephen Hawking, called the area theorem. It stated that the surface area of a black hole's event horizon can never decrease. The area of the event horizon always increases or stays the same. This sounded familiar. It was strikingly similar to the second law, where entropy always increases. Bekenstein saw this parallel and made a bold suggestion. What if a black hole's entropy is its surface area? He proposed that the universe obeys a generalized second law of thermodynamics. The entropy of everything outside the black hole, plus the entropy of the black hole itself, can never decrease. And the black hole's entropy, he claimed, was proportional to the area of its event horizon. When something falls in, the entropy outside goes down, but the black hole's area, and thus its entropy, increases by a greater amount. The law is saved. When Bekenstein first presented this, the physics community was skeptical. How could an area, a geometric property, represent a statistical quantity like entropy? The idea had another, stranger implication. If an object has entropy and energy, it must have a temperature. If a black hole has a temperature, it must radiate heat. And everyone understood that nothing could escape from a black hole. The idea seemed to be a dead end. Its most powerful critic was the man who had discovered the area theorem in the first place, Stephen Hawking. Hawking was not convinced. He thought the similarity between his area theorem and the second law was just a coincidence. The idea that a black hole could have a temperature and radiate energy seemed absurd. It went against the very definition of a black hole. In 1973, he set out to prove Bekenstein wrong. Hawking applied the rules of quantum mechanics to the space just outside an event horizon. In quantum theory, what we see as empty space is a simmering soup of virtual particles. Pairs of particles and antiparticles pop into existence, exist for a moment, and then annihilate each other. Hawking considered what would happen if a pair appeared right at the edge of a black hole. Occasionally, one particle would fall in, while its partner would escape. The particle that fell in is lost forever. Its partner, now alone, becomes a real particle. To a distant observer, it would look as if the black hole itself had just emitted a particle. The energy for this new particle has to come from somewhere. Hawking realized it is taken from the black hole itself. The particle that falls in carries negative energy from our perspective, reducing the black hole's total mass. Hawking was stunned by his own calculations. He had tried to show that black holes could not radiate, but his work proved they must. This slow trickle of particles is now called Hawking radiation. For large black holes, the effect is incredibly slow. But the crucial point was that they do radiate. And the nature of this radiation was thermal. It had the exact spectrum of a perfect radiator, an object in thermal equilibrium. If something has thermal radiation, it must have a temperature. Against his own intentions, Hawking had proven that Bekenstein was right. Black holes have a temperature. And if they have a temperature and entropy, they are thermodynamic objects, subject to the same laws as everything else. Hawking was even able to calculate the exact value of a black hole's entropy. The result was simple and profound. The formula that emerged from their work is one of the most important in modern physics. It is engraved on Stephen Hawking's memorial stone, a testament to its significance. It is the Bekenstein-Hawking formula, and in its simplest form, it reads: S equals A divided by 4. S is the entropy of the black hole. A is the surface area of its event horizon. This confirms Bekenstein's idea. A black hole's entropy is proportional to its surface area. This is strange. For every other object in the universe, entropy is proportional to its volume. A bigger box of gas has more room for disorder. But for a black hole, the disorder is not stored in its three-dimensional volume. It is encoded on its two-dimensional surface. This leads to a second, mind-bending consequence. Black holes contain a colossal amount of entropy. The formula implies that a black hole packs in the maximum possible entropy for any object of its size. If you were to calculate the entropy of the Sun, you would get a very large number. But if you crushed the Sun into a black hole a few kilometers across, its entropy would be about 10 trillion times larger than the entropy of the original Sun. A supermassive black hole at the center of a galaxy has an entropy that is incomprehensibly larger than the entropy of all the stars in that galaxy combined. The disorder on the surface of that single object dwarfs the disorder of everything else. This is the solution to the paradox. Black holes do not destroy entropy. They are its greatest repositories. When you throw your high-entropy cup of tea into a black hole, the total entropy of the universe increases, because the black hole's surface area grows by an amount far greater than the entropy you threw in. The law was never broken. The suspect was not only innocent, but was the ultimate enforcer of the law it was accused of violating. Black holes are not simple. They are cosmic ledgers, storing a record of all the chaos they have ever consumed. The story does not end there. Sometimes, black holes collide. Observatories like LIGO have now witnessed the gravitational waves from these events. And these mergers offer dramatic proof that black holes are governed by entropy. When two black holes merge, they form a single, larger black hole. The area theorem implies that the surface area of the final black hole must be greater than the sum of the areas of the two original black holes. The entropy of the final black hole is greater than the sum of the entropies of its parents. The merger creates a massive amount of new disorder. But recent research has proposed something even more profound. An idea called the maximum entropy conjecture suggests that the final black hole that forms from the merger settles into the exact state that gives it the absolute maximum possible entropy. Like water flowing down a hill until it reaches its lowest point, a black hole merger violently rearranges itself until it finds its state of maximum entropy. By simply calculating this point of maximum entropy, researchers can predict the mass and spin of the final black hole with remarkable accuracy, matching the results of powerful computer simulations. Thermodynamics is not just a passive record of disorder. It appears to be an active, guiding principle in even the most extreme gravitational events. The discovery that a black hole's three-dimensional information is stored on its two-dimensional surface was the seed of another idea, one that continues to reshape physics: the holographic principle. It takes the lesson of the black hole and applies it to the entire universe. If a 3D volume can have all its information encoded on a 2D surface, could the same be true for the cosmos? The principle suggests that everything we experience in 3 dimensions might be a projection of information stored on a vast, distant, 2-dimensional surface that surrounds us. Like a hologram on a credit card, a flat film could produce a full 3D image. This sounds like fiction, but it has become a serious and powerful tool for physicists. It suggests a duality. A difficult problem in our 3D world of gravity could be translated into a simpler problem without gravity on the 2D surface. This correspondence has offered a potential path toward understanding the black hole information paradox, which asks what truly happens to information that falls into a black hole. We do not yet know if the holographic principle is the final truth of our reality. But it all began with that simple question about disorder and a black hole. It started with the slow realization that the most chaotic, information-packed places in the universe are the silent, dark, and deceptively simple surfaces of black holes. So, a room can be messy. But its disorder is nothing compared to the chaos locked away on the surface of a black hole. We began with a puzzle. Black holes seem to be deleting entropy, threatening a fundamental law of physics. We followed the work of Bekenstein and Hawking, who not only resolved the paradox but revealed a deeper truth. Black holes are not destroyers of information, they are its quiet guardians. They are not pristine voids of simplicity. They are the most complex and entropy-rich objects the universe can create. Their entropy is written on their surface, a discovery that hints at the very nature of reality itself. The next time you look into the night sky, remember that the quiet darkness between the stars holds objects of unimaginable chaos. They are the true champions of disorder, the ultimate keepers of the universe's messy secrets, reminding us that in the cosmos, profound complexity often hides behind the simplest of faces. If this quiet exploration of the universe helps you see things in a new way, consider liking the video and subscribing for more journeys into physics and cosmology. And feel free to share in the comments what other cosmic mysteries you find compelling. Thank you for watching. The law that will end the universe. There is a quiet rule that governs everything in existence, from the atoms in our bodies to the most distant galaxies. It points in only one direction, toward stillness and decay. It suggests that the universe itself has a final chapter. So, what does this cosmic principle mean for the future of reality, and how will the story end? Think of a cup of hot coffee on a cold morning. You can see the steam rising from it. That cup is a small, ordered pocket of energy in a cooler room. What happens next is something we take for granted, because it always happens. The coffee cools. The heat moves out into the air, the molecules slow down, and the energy spreads until the cup and the room are the same temperature. The process never goes in reverse. You will never see a cool cup of coffee spontaneously draw heat from the air to become hot again. This simple, everyday observation is a glimpse into one of the most fundamental laws of the cosmos. A law that guides not just coffee, but stars, galaxies, and the entire universe toward a final, inescapable state. This is the second law of thermodynamics, and its core idea, entropy, is the engine of cosmic change. It is the law that will end the universe. The arrow of time. To understand the universe's ultimate fate, we have to understand its tendencies. And the second law of thermodynamics describes one of its most persistent. It says that in an isolated system, and the universe is the ultimate isolated system, the total amount of disorder, or entropy, will not decrease. In any real-world process, it always increases. This quiet, one-way movement toward disorder is what physicists call the arrow of time. It is the reason we remember the past but not the future. The past is the past because it was a more ordered state. The universe began in an incredibly organized, low-entropy state at the Big Bang, and the entire history of the cosmos has been the story of that initial order slowly and unstoppably unraveling. Think of it like this. Imagine a sandcastle, carefully built. That is a state of low entropy, ordered and complex. Over time, the wind and waves arrive. The castle crumbles back into a simple, disordered pile of sand. There are countless ways for the sand to be a disordered pile, but very few ways for it to be that specific castle. The universe naturally moves toward the states that are most probable, and there are always more ways to be disordered than to be ordered. A broken glass on the floor has higher entropy than a whole glass on the table because its pieces can be scattered in a near infinite number of arrangements. You will never see those pieces spontaneously leap from the floor and reassemble themselves, because that would require a statistically impossible decrease in entropy. This idea was given a mathematical form in the 19th century by the physicist Ludwig Boltzmann. He defined entropy as a measure of the number of possible microscopic arrangements a system can have while still appearing the same on a large scale. Let's return to the coffee. Its macrostate is its temperature. When it's hot, the fast-moving molecules are concentrated in the cup, a relatively small number of possible arrangements. As it cools, that energy spreads to the trillions of air molecules in the room. The number of ways that energy can be distributed among all those molecules, the number of microscopic states, grows to an unimaginably large figure. The system has moved from a state of low probability to a state of high probability. And it will not go back. This is the principle at work everywhere. A car rusting, a mountain eroding, a star burning its fuel. They are all processes that increase the overall entropy of the universe. Life itself can seem like an exception. Organisms take in energy and create incredibly complex, ordered structures. But this local order comes at a great cost. To build and maintain themselves, living things must consume energy and radiate waste heat into their surroundings, dramatically increasing the total entropy of the universe. Life is a temporary, beautiful eddy in a river that flows inexorably toward a sea of universal stillness. We are part of a process that is destined to run down. The second law is not just a rule about engines and coffee cups. It is the quiet conductor of the cosmic orchestra, and its final performance is a gradual, irreversible fade into silence. It tells us that the structures and energy we see around us today are temporary. They are all destined to dissipate until the entire cosmos reaches a state of perfect, uniform balance. This final state is what physicists call the heat death of the universe, a state of maximum entropy from which nothing can change. To understand how we get there, we must first journey into a strange and unexpected connection, the link between this physical decay and the nature of information itself. Information and disappearance. The story of entropy took an interesting turn in the mid-20th century, far from steam and stars, in the world of codes and communication. In 1948, a mathematician named Claude Shannon was trying to understand the fundamental nature of information. He wanted to quantify the idea of surprise in a message. His answer came in a formula that looked surprisingly similar to Boltzmann's formula for thermodynamic entropy. Shannon's information entropy measures the average uncertainty in a piece of data. Imagine a coin that is rigged to always land on heads. A message telling you the outcome of a flip contains no information, because there is no uncertainty. The entropy is zero. Now, imagine a fair coin, with two equally likely outcomes. A message telling you the result resolves that uncertainty. Shannon defined this amount of information as 1 bit. A random, unpredictable message has high entropy, it is full of surprises. A repetitive, predictable message has low entropy. So what is the connection? Why do these two ideas, the physical disorder of particles and the uncertainty in a message, share the same mathematical foundation? The bridge is the idea of missing information. High thermodynamic entropy means a system has a huge number of possible microscopic arrangements that all look the same from the outside. If you only know the temperature of a room, you have very little information about the exact position of any single molecule. Your ignorance, your missing information, about the true state of the system, is a direct measure of its thermodynamic entropy. A system at maximum entropy is one where you are maximally ignorant of its microscopic details, because there are just so many possibilities. This link becomes powerful when we consider a famous thought experiment from the physicist James Clerk Maxwell. This is the story of Maxwell's demon. Imagine a box of gas, divided by a wall with a tiny door. A demon sits at this door, watching the molecules. When a fast-moving, hot molecule approaches from the right, it opens the door to let it through to the left. When a slow-moving, cold molecule approaches from the left, it lets it pass to the right. Over time, the demon sorts the molecules, making one side hot and the other cold. This creates order, lower entropy, seemingly from nothing. It appears to violate the second law. For over a century, this paradox remained. The solution arrived in 1961, when a physicist named Rolf Landauer looked at the problem from the perspective of information. The demon isn't just sorting molecules, it's gathering information. It has to measure each molecule and store that data in its memory. As the demon acquires information, its own internal memory fills up. Its own entropy increases. To keep working, the demon must eventually erase its memory to make room for new measurements. This was the key insight. Landauer's principle states that the act of erasing information is not free. It has a fundamental, unavoidable thermodynamic cost. Erasing one bit of information must release a minimum amount of energy into the environment as heat. This release of heat increases the entropy of the surroundings. It turns out that the increase in entropy from erasing the demon's memory is always greater than or equal to the decrease in entropy from sorting the gas. The second law is saved. The total entropy of the whole system, gas and demon, always increases. Information, Landauer showed, is physical. It is tied to the thermodynamic reality of the universe. Every time you delete a file, a tiny, almost immeasurable puff of heat is released, a small contribution to the universe's ever-growing entropy. If this quiet exploration of the universe's ultimate fate is something you find interesting, consider subscribing to the channel. We are about to follow this law to its final conclusion, from our vibrant present to the unimaginable stillness of the far future. The era of starlight. We are living in a special, though temporary, moment in cosmic history. Astronomers call it the stelliferous era, the star-bearing era. It began when the first stars ignited, and it will continue for as long as stars shine. Our universe is currently filled with light, heat, and complexity. Galaxies are vast, swirling collections of stars, and these stars are the universe's great engines. They are wonderful examples of local order. Through gravity, they gather disordered clouds of gas and compress them into dense, highly structured spheres. But this creation of order comes at a great cosmic price. A star, like our Sun, maintains its structure by burning through its nuclear fuel. In doing so, it radiates an enormous amount of energy, heat and light, out into the cold emptiness of space. This radiation spreads out, dissipates, and contributes immensely to the total entropy of the universe. The order of a single star is paid for with a vast amount of cosmic disorder. The rule is always followed. The stelliferous era is defined by the process of star formation. But this process is finite. The universe began with a limited supply of hydrogen and helium. Every star that forms uses up some of that material. The universe's most active period of star formation is already behind us, a peak that passed many billions of years ago. Like a great fire that has already burned through its easiest fuel, the overall rate of star birth is slowly declining. The fate of this era is written in the lives of its final stars. The most massive stars burn brightly and disappear quickly. Sun-like stars have lifespans of around 10 billion years. But the true marathon runners are the red dwarfs. These are small, dim stars, and they use their fuel so slowly that they can live for trillions of years. As we look to the far future, one by one, the brighter stars will burn out. The sky will grow darker and redder. For an immense stretch of time, these red dwarfs will be the only sources of light in the cosmos. A civilization living trillions of years from now, if one existed, would look up at a sky dominated by these dim, ancient embers. But even their time is limited. Eventually, around 100 trillion years from now, the very last red dwarf will use up its fuel. The last light from the last star will flicker out. The stelliferous era will end. The universe will fall into a profound and permanent darkness, populated only by the cooling remnants of the stars that once gave it light. This is the beginning of the next great cosmic age, the degenerate era. An empire of remnants. 100 trillion years have passed. The last star has gone out. The universe is now a dark, cold, and vastly expanded space, a silent expanse filled with the remnants of the stelliferous era. Astronomers call this material degenerate matter, a term for matter crushed to incredible densities. This is the degenerate era. The inhabitants of this universe are the ghosts of stars. There are black dwarfs, the cold, crystallized remnants of stars like our Sun. There are neutron stars, the ultra-dense cores left behind by supernovae. And there are black holes, born from the collapse of the most massive stars. These objects, along with any planets that survived the death of their stars, drift silently through the darkness. For a time, gravity will continue its work. Over unimaginable timescales, some of these stellar remnants will be flung out into the void between galaxies. Others will spiral inward, consumed by the supermassive black holes at the centers of galaxies. Galaxies themselves will slowly dissolve. But an even more fundamental process is at work, one that targets the substance of matter itself. Some theories of particle physics suggest that protons, the building blocks of atoms, are not truly stable. They are predicted to have an incredibly long, but finite, lifespan. Over a timescale so vast it is difficult to comprehend, perhaps 10 to the power of 34 years or even longer, protons are expected to decay into lighter particles. In the vastness of the degenerate era, time is all the universe has. As this process unfolds, matter as we know it will begin to dissolve. The black dwarfs, neutron stars, and frozen planets will slowly evaporate into a thin soup of radiation and elementary particles. It is like imagining a statue made of sugar left in a light drizzle for 1,000,000 years. The process is imperceptibly slow, but the outcome is inevitable. The statue vanishes. In the same way, all the degenerate matter that once formed stars and planets will be erased. After perhaps 10 to the power of 40 years, the process is complete. The universe is now almost entirely empty. The great cosmic structures are gone. The matter that built them has decayed. All that remains are the most stable objects the universe has ever produced, black holes. And so begins the next, and longest, chapter. The last kings. We have now moved forward in time to roughly 10 to the power of 40 years. The degenerate era has ended. All normal matter has decayed away. The universe is an almost perfect vacuum, colder and darker than we can imagine. Dotted throughout the immense darkness are the last remaining titans of the cosmos, the black holes. This is the black hole era. For a long time, it was believed that black holes were eternal prisons of matter and energy. If this were true, the universe would simply consist of black holes drifting ever farther apart in an empty void, forever. But in 1974, Stephen Hawking made a discovery that changed our understanding of the universe's final fate. By combining general relativity with quantum mechanics, Hawking showed that black holes are not completely black. Due to quantum effects at their event horizon, they should emit a faint trickle of radiation. This phenomenon, now known as Hawking radiation, means that black holes have a temperature. And because they radiate energy, they must be losing mass. Very, very slowly, black holes evaporate. The process is astoundingly slow. The temperature of a black hole is related to its mass. The bigger it is, the colder it is, and the slower it evaporates. A black hole with the mass of our Sun would take around 10 to the power of 67 years to disappear. The supermassive black holes at the centers of galaxies will take much longer, up to 10 to the power of 100 years, a number known as a googol. During the black hole era, these objects will be the only organized structures left. They are the final repositories of order. As they radiate, they slowly convert their mass back into energy, increasing the universe's entropy. The end of a black hole's life is ironically sudden. As it loses mass, its temperature rises, and its rate of evaporation speeds up. In its final moments, a black hole that has been slowly dying for a googol years will release its remaining mass in a final burst of energy. Now, picture the scene. Across the unimaginable emptiness, the last of the small black holes have vanished. We are waiting for the very last, most massive supermassive black hole in the entire universe to die. After an eternity of silence, it happens. A final, lonely burst of light. And then, nothing. With the evaporation of the last black hole, the black hole era ends. The last organized matter is gone. The universe enters its final, eternal phase. The final stillness. We are now beyond 10 to the power of 100 years. The last black hole has evaporated. The universe has reached the end of its story. This is the dark era. It is the state of maximum entropy that physicists call the heat death. There are no more structures. No stars, no galaxies, no black holes. Nothing is left that can undergo any meaningful change. The universe is a vast, cold, and uniform void. Drifting aimlessly through this emptiness is a thin, featureless soup of fundamental particles. Photons with enormous wavelengths, neutrinos, and a sparse scattering of electrons and positrons. The temperature of the universe will be almost, but not quite, absolute zero. And because of the continued expansion of space, it will grow colder still, approaching zero forever but never reaching it. The universe has reached a state of thermodynamic equilibrium. Energy is spread perfectly evenly. There are no hot spots and no cold spots. Without any temperature differences, energy cannot flow, and no work can be done. For all practical purposes, nothing will ever happen again. In this final state, time itself loses its meaning. The arrow of time, which points in the direction of increasing entropy, has nowhere left to point. The universe is already in its maximum state of disorder, so there is no forward for time to flow. The concept of change, of past, present, and future, becomes irrelevant. The cosmos will be locked in this timeless, static state for eternity. It will not end with a dramatic event, but with an eternal silence. This is the ultimate, humbling prediction of the second law of thermodynamics. A journey from an ordered, energetic beginning to a final state of complete stillness. While some other ideas exist, the heat death remains the most accepted outcome based on the physics we know today. We have journeyed from a simple cup of cooling coffee to the edge of time. We have seen how a quiet law of physics, the steady increase of entropy, points everything in existence toward decay and stillness. We have walked through the era of starlight, the long night of the degenerate era, and the lonely reign of the black hole era, all leading to one final state: the heat death of the universe. So, what are we to make of this? Does this cosmic end render our existence meaningless? Does the fact that the universe will one day fall silent mean that our lives and achievements are all just a fleeting event, destined to be erased? Perhaps not. Perhaps the opposite is true. The laws of physics tell us that the universe we inhabit right now, this vibrant, complex, starlit era, is an incredibly special and temporary phase. We are living in the universe's brilliant youth. We are the lucky ones, here to witness a brief cosmic moment between the initial fire and the final ice. We are, in a very real sense, the universe's way of seeing its own splendor. The knowledge that this moment is finite does not have to be a source of despair. It can be a source of appreciation. It makes the light of the stars more brilliant, the complexity of life more miraculous, and the present moment infinitely more precious. The universe may be destined for an endless, quiet night, but we are here for the dawn. And that is a truly wonderful thing. The story of the universe's end is tied to its beginning. To see how this incredible journey started, you can watch our video on the Big Bang. And if you enjoy these quiet explorations into the biggest questions in the cosmos, consider subscribing to the channel. Why scientists are rethinking the end of the universe. For a long time, we have held a quiet, accepted story about how the universe ends. A slow fading into cold and stillness. It was called the heat death, a final chapter where all things grind to an eternal halt. This was not a myth or a guess, but a vision of cosmic destiny rooted in the most fundamental laws of physics. A forecast of ultimate darkness that we learned to see as inevitable. But what if that story is wrong? What if the end is not a gentle fade, but a violent tearing apart of reality itself? Or something stranger still, a kind of cosmic reset? In the last few years, a series of quiet discoveries have begun to appear, small cracks in our understanding of the cosmos. New data arrives from our most sensitive instruments, and it seems to be telling a different story. One that points to a far stranger, and perhaps more dramatic, fate for our universe. This is the story of why scientists are being forced to rethink the end of everything. Welcome. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing. And wherever you find yourself right now, feel free to share where you're listening from. To see why the picture of the end is changing, we first have to understand the picture we've held for so long. It is a concept known as the heat death, or the Big Freeze. It is less of a single event and more of a slow, unfolding process. It begins not with spectacle, but with an observation from everyday life. Imagine holding a warm cup of tea in a cool room. The concentrated heat from the tea does not stay where it is. It radiates outward, spreading into the air around it. The tea cools, the room warms, and after a time, everything settles at the same lukewarm temperature. Nothing is hot, and nothing is cold. It is a state of balance, of stillness. Now, imagine that same principle playing out not in one room, but across the entire, unimaginable vastness of the universe. That, in its essence, is the heat death. This forecast comes from one of the most powerful laws in physics, the Second Law of Thermodynamics. It says that in a closed system, and the universe is the ultimate closed system, a quantity called entropy always tends to increase. But what is entropy? It is often called disorder, but a better way to see it is as a measure of how spread out energy becomes. Think of a new deck of cards, ordered perfectly by suit and number. This is a low entropy state. Now, shuffle the deck. The cards are mixed, chaotic. This is a high entropy state. And if you keep shuffling, the cards will never spontaneously return to their original, ordered arrangement. The universe works in a similar way. It is constantly shuffling its energy. We see this shuffling everywhere. An ice cube in hot tea melts as the tea cools. The fast-moving molecules of the tea transfer their energy to the slow-moving molecules of the ice until everything reaches a uniform temperature. This final state is called thermal equilibrium. It is a state where no temperature differences are left to drive any action. No heat flows from hot to cold. It is a state of maximum entropy. Right now, our universe is a place of spectacular energy differences. Blazing hot stars pour energy into the freezing vacuum of space. Gravity pulls matter together into dense galaxies. These differences, between hot and cold, dense and empty, are what allow work to be done. They power the fusion in stars, the formation of planets, and the complex chemistry of life. But the universe is not still. It is expanding, and in 1998, astronomers found that this expansion is not slowing down as everyone expected. It is accelerating. An unknown, unseen influence, which scientists have named dark energy, is pushing the fabric of space apart. This accelerating expansion is the engine of the heat death. As space stretches, the energy within it becomes more and more diluted. Over trillions of years, the gas needed to form new stars will be exhausted. The stars we see today will burn out, collapsing into the cold embers of white dwarfs, neutron stars, and black holes. The universe will enter a degenerate era, a ghostly realm populated only by the corpses of stars. The story continues even from there. Over truly unimaginable timescales, even these remnants will decay. Protons themselves may dissolve into a sea of radiation. And the most stable objects of all, black holes, will slowly evaporate through a quantum process called Hawking radiation, leaking their energy back into the void over googles of years. Eventually, after a time so long it resists human comprehension, the universe will approach its final state. A vast, dark, and uniform soup of stray particles, all at a temperature just above absolute zero. This is maximum entropy, thermal equilibrium on a cosmic scale. In this state, no work can be done. No stars can shine, no life can exist. The concepts of heat and motion become meaningless. Because entropy can no longer increase, some argue that time itself would lose its direction. The universe would be left in a state of perfect, eternal stillness. This has been the standard, accepted story of our cosmic end. A slow, quiet, and definitive finale. For decades, the heat death was the foundation of our scientific study of the end. It was a clean, logical conclusion. But science is a restless process of questioning and revising. And recently, that cherished model has begun to show some serious cracks. The first clue that something might be different comes from the expansion of the universe itself. This expansion is measured by a number called the Hubble constant. The difficulty is, we have two very precise ways of measuring this constant, and they give two different answers. This disagreement is known as the Hubble tension, and it is one of the great puzzles in cosmology today. The first method looks at the early universe, in the faint afterglow of the Big Bang. Using our standard model of physics, scientists can predict what the expansion rate should be today. This method consistently arrives at a value around 67 or 68 kilometers per second per megaparsec. The second method looks at the late universe, closer to us in time and space. By observing objects like Type Ia supernovae, exploding stars whose brightness is known, astronomers can directly measure the current expansion rate. These measurements, supported by instruments like the James Webb Space Telescope, point to a higher value, around 73 or 74. The difference between 67 and 73 may not sound large, but the measurements are now so precise that the two values seem fundamentally incompatible. It suggests that either our understanding of the early universe is incomplete, our measurements of the late universe have some hidden flaw, or, the most intriguing possibility, our standard model of the cosmos is missing something important. The Hubble tension challenges our assumptions. If the expansion rate is not what we think, or if it has changed in unexpected ways, then our neat timeline for the heat death could be wrong. This leads to the second, deeper crack in the story. The nature of dark energy, the mysterious substance that makes up 68% of the universe and drives its acceleration, is almost completely unknown. For years, the simplest model was that dark energy is a constant property of space itself. In this scenario, the heat death is the clear outcome. But what if dark energy is not constant? What if it changes over time? This possibility is known as quintessence, where dark energy is a dynamic, evolving field. Some of our latest cosmic surveys are hinting that this might be the case. The Dark Energy Spectroscopic Instrument, or DESI, has created a map of the universe of unprecedented detail. Early analysis of this data suggests that a simple, unchanging dark energy might not be the best fit. The data does not prove it, but it hints that the strength of dark energy might be evolving. If dark energy does change, it throws the future of the cosmos into question. The end is no longer a settled forecast. It becomes an unpredictable story with several possible endings. One is the Big Rip. In this scenario, dark energy grows stronger over time. This hypothetical, phantom energy, would cause the expansion to become uncontrollable. First, galaxy clusters would be pulled apart. Then, gravity holding individual galaxies together would fail. In the final moments, the force would become so strong it would overwhelm the forces holding atoms themselves together. Space-time would be torn apart. On the other hand, if dark energy weakens, gravity could again become the dominant force. This would lead to a big crunch. The expansion would slow, stop, and then reverse. Galaxies would rush back together. The universe would contract, growing hotter and denser until it collapsed back into an infinitely hot, infinitely dense singularity, much like the state from which it began. These are no longer fringe ideas. They are serious possibilities, because our observations are forcing us to consider them. The quiet picture of a universe fading away is being challenged by the messy, contradictory data we are now gathering. While some scientists explore new endings, others are re-examining the heat death itself. They have found a fascinating wrinkle in the laws of thermodynamics, one that suggests the universe may not be destined for perfect equilibrium after all. The classic heat-death analogy of a closed box is flawed. The universe is not a box with fixed walls, its boundaries are expanding. This changes the calculation in an important way. The cosmologist David Laser identified something he called the entropy gap. He pointed out that as the universe expands, the maximum possible entropy the universe could have increases. Because the universe is expanding so rapidly, this ceiling for maximum entropy is rising faster than the actual entropy of the universe can keep up. This creates a persistent gap between the actual entropy and the theoretical maximum. It is this gap that allows for the creation of order. Gravity is the architect of this process. While thermodynamics pushes things toward a smooth, uniform state, gravity does the opposite. It pulls a diffuse cloud of gas into dense, ordered structures like stars and planets. This process actually increases the total entropy of the universe, because a star radiates enormous amounts of disorganized heat and light into the cold of space. Gravity, in effect, exploits the entropy gap, creating pockets of complexity while still obeying the second law on a global scale. Life is another example of this principle. A living being is an island of intricate order. You maintain your structure by taking in energy from your environment and exporting waste heat, a high-entropy form of energy. You are a walking, thinking pocket of low entropy, and you maintain that state by increasing the overall entropy of the universe around you. The key insight is that the heat death, as a final state of perfect equilibrium, might be a target the universe never reaches. As long as expansion creates new space faster than entropy can fill it, the potential for order might never vanish. The cosmologist Sean Carroll argues that in an eternally expanding universe, there is no true maximum entropy state. The universe just keeps evolving. Even after all the stars have burned out and the black holes have evaporated, the vacuum of space will still possess dark energy, causing the expansion to continue forever. This empty space is not a dead end. It is a dynamic environment where change can continue. This perspective reframes the end. Instead of a final stop, the universe's future could be one of infinite, ongoing transformation. The death in heat death may not be an end to all organization, but a transition to a new cosmological phase. The lights of the stars will go out, but the potential for structure, and perhaps even consciousness, may not. The entropy gap provides a loophole, a quiet possibility that the story of the universe is not one of simple dissolution, but of perpetual, unending change. We have journeyed through the cold fade of heat death and the violent possibilities of a rip or a crunch. We have explored a loophole where order might persist. But now, we must venture into the strangest territory of all, the realm of quantum mechanics. Here, we find possibilities that suggest the end may not be an end at all, but a prelude to a new beginning. Our guide is the black hole. We once thought of them as points of no return. But Stephen Hawking showed that due to quantum effects, black holes are not truly black. They emit a faint thermal glow, now called Hawking radiation. This causes them to slowly lose mass and, over unimaginable timescales, evaporate completely. A supermassive black hole might last for 10 to the power of 100 years, but even it is not eternal. Hawking radiation proved that even the most stable objects in the universe are subject to decay. Imagine our universe in the dark era, trillions of years from now. The stars have died. The black holes have evaporated. The universe is a cold, dark, and almost perfectly empty void. It seems like the end. But almost empty is the key. The vacuum of space, according to quantum field theory, is not truly empty. It is a foam of quantum fluctuations, where pairs of virtual particles pop into existence from nothing before annihilating each other. These are not theoretical ideas, we see their effects in labs today. Normally, these are tiny, fleeting events. But in the deep future, the universe has a near infinite amount of time. And with enough time, the improbable becomes inevitable. This leads to an idea known as Poincare recurrence. In any finite system, if you wait long enough, the random motions of its particles will eventually cause them to return to a state very close to their original one. It is like shuffling a deck of cards for an eternity. Eventually, by pure chance, the cards will return to their original, ordered state. In the cold void of the far future, random quantum fluctuations will continue. Most will be small, but if you wait long enough, a timescale that makes the life of a black hole seem like the blink of an eye, a colossal fluctuation could occur. A fluctuation so large that it could spontaneously arrange particles into a highly ordered, low-entropy state. Wait long enough, and you could get a rock. Wait longer, and you could get a Boltzmann brain, a conscious mind with false memories. Wait for a truly staggering amount of time, and you could, in theory, get the ultimate quantum fluctuation. A spontaneous drop in entropy so immense that it creates a state of matter dense enough to trigger a new Big Bang. In this scenario, a new universe could be born from the quantum vacuum of our dead one. Our universe may not be the first, and it may not be the last. A related possibility is vacuum decay. This theory suggests that our universe might exist in a false vacuum, a state that is stable for now, but not permanently. Like a ball resting in a small dip on the side of a large hill. A single quantum fluctuation could nudge a region of our vacuum into the true, lower energy state. If this happened, a bubble of this true vacuum would expand at the speed of light, rewriting the laws of physics as it went. While this sounds like annihilation, some theories suggest the energy released could itself trigger a new Big Bang. These quantum scenarios shatter our classical ideas of a final end. They introduce the ultimate wildcard, the possibility that even from absolute nothingness, a new creation can arise. We began this journey with a single forecast, the heat death. A universe fading into a cold, eternal equilibrium. But as we've traveled to the frontiers of cosmology, we've found that this story is anything but settled. The final chapter of the universe is not only unwritten, the entire book is being revised. We have seen how a quiet disagreement in our measurement of cosmic expansion casts doubt on the entire timeline of our universe's fate. We have looked into the mystery of dark energy and learned that its nature is one of the greatest unknowns in science. Depending on how it behaves, our universe could be headed for a violent rip, a fiery crunch, or a slow fade. We've explored the subtle beauty of the entropy gap, a consequence of our expanding universe that offers a loophole against ultimate disorder. It reframes the end not as a final stop, but as a perpetual transformation, where the potential for complexity and order may never be extinguished. And finally, we ventured into the quantum world, where we found that even in a dead, empty void, the ceaseless fizz of quantum fluctuations holds the potential for cosmic rebirth. So, why are scientists rethinking the end of the universe? Because at every turn, new discoveries are revealing that our cosmos is more complex and far stranger than our simplest models predicted. The picture of a slow, simple fade has been replaced by a branching tree of wild possibilities. The end of the universe is no longer a question of when, but a profound mystery of what. This journey leaves us not with an answer, but with a sense of wonder. It reminds us that science is not a collection of facts, but a living process of inquiry. The universe is not a closed book, but a story that is still being told. We are fortunate to live in a time where we can read some of its pages and glimpse the astonishing possibilities that lie ahead. The final fate of our universe remains one of the greatest unsolved mysteries, a testament to the depth of the cosmos and the enduring power of human curiosity to explore it. Why a perfect universe would be a nightmare. Forget, for a moment, the idea of utopia. Imagine a universe where nothing ever broke, where every star burned with the same, steady light for eternity. A place where nothing faded and nothing ever ended. It has the sound of a paradise. But it would be something else entirely. A quiet prison, frozen in an eternal, unchanging now. In the next few minutes, we will explore why this perfect universe might be a silent nightmare, and why the universe's relentless, often chaotic, journey towards decay may be the most beautiful thing that could have ever happened. The prison of perfection. There is a quiet, human instinct that seeks out perfection. We look for it in our art, in our engineering, and in ourselves. We imagine a world without flaws, a state of complete harmony and order. So it is no surprise that when we look out at the cosmos, we see something that looks like an impossible level of perfection. Physicists refer to it as the fine-tuning of the universe. It is the observation that the fundamental constants of nature, the strength of gravity, the charge of an electron, the rate at which the universe expands, appear to be balanced on a razor's edge. If the force of gravity were different by even a minuscule amount, life-sustaining stars like our Sun simply could not exist. If the initial expansion after the Big Bang had been microscopically stronger or weaker, the universe would have either collapsed back on itself almost instantly, or expanded so fast that not a single star or galaxy could form. It seems the universe isn't just hospitable to life, it is so exquisitely tailored for it that it stretches belief. This observation has led many to wonder if we are the product of a deliberate design, or perhaps the beneficiaries of a multiverse where countless other, lifeless universes exist with the wrong settings. We won a kind of cosmic lottery. From this perspective, perfection seems like a prerequisite for our existence. It feels like a gift. But what if we have been asking the wrong question? What if the real question is not why the universe seems so perfect for us, but what would happen if that perfection was absolute? Let us run a quiet thought experiment. Let us not just imagine a universe fine-tuned for life, but a universe that has reached a state of ultimate, unshakable order. A universe where the drive towards perfection has won completely. A world without flaw, without change, without decay. What would that actually look like? It would not be a bustling utopia. It would be a silent, static photograph. Imagine waking up in this world. You pour a cup of coffee. The steam rises, forming intricate swirls in the air, and then it freezes. The steam cloud hangs there, motionless, a permanent sculpture of water vapor. The coffee in your mug never cools. Heat, in this universe, does not flow from hot to cold, because that would be a change, a movement towards a more disordered state. Everything remains in its perfect, isolated condition. You drop an ice cube into a glass of water. It does not melt. The rigid, ordered structure of the ice is a state of lower entropy of higher order. The warmer, more chaotic water molecules have no impulse to break it down. The ice cube would sit there, unchanged, for all of eternity. In your home, dust never settles. Paint never peels. The pages of your books never yellow with age. A dropped glass would not shatter, it would remain perfectly intact. At first, this might seem wonderful. No maintenance, no loss. But a sense of unease would begin to settle in. You would notice that the world outside is also frozen. The leaves on the trees are perpetually green, never decaying to enrich the soil. The clouds are painted onto the sky. The sun burns with a steady light, but its energy never truly dissipates to warm planets and drive weather. In this universe, there is no forward momentum. No arrow of time. Physicists like Sean Carroll have explained that our very perception of time's flow is linked to the universe's journey from order to disorder. We remember the past because it was in a lower entropy, more ordered state. The egg was whole. We anticipate the future because it will be in a higher entropy, more disordered state. The egg will be scrambled. The increase of entropy is the clock that ticks for the entire cosmos. In a perfect, static universe, that clock does not tick. There is no distinction between past and future, no cause and effect, only a permanent, unchanging, is. Consider what this means for life itself. Life is a process of constant change. Our bodies build new cells, break down old ones, and heal from injuries. All of these processes require the transformation of energy. We take in ordered, low-entropy energy, as food or sunlight, to maintain the incredible order of our bodies. But in doing so, we release disordered, high-entropy energy as heat back into the environment. Life, as we will see, is not a rebellion against disorder. It is an engine for creating it. In a perfect universe, this engine cannot run. A wound would not heal, it would simply remain. Your body would not age, but neither would it grow. You would be trapped in a single, unchanging biological moment. On a cosmic scale, the nightmare deepens. Stars, the great engines of the cosmos, would become eternal monuments. Our sun shines because it is engaged in a messy, violent process of turning the ordered structure of hydrogen into helium, releasing a colossal amount of chaotic energy. In a perfect universe, this process would halt. Stars would simply be perfect, unchanging spheres of plasma. There would be no supernovas. The death of massive stars is a chaotic event that scatters newly forged heavy elements across the galaxy. Without these explosions, the carbon in our bones, the oxygen we breathe, and the iron in our blood would not exist. The universe would be composed of little more than the simple hydrogen and helium from its birth. This is the terror of true perfection. It is a prison of timelessness. A universe without a story, without the very possibility of becoming. The beauty and meaning of our existence are born not from the universe's perfection, but from its fundamental, glorious flaw. And that flaw has a name: entropy. The glorious flaw. To understand why a perfect universe would be a nightmare, we need to understand the one law of physics that makes our dynamic, beautiful universe possible: the second law of thermodynamics. At its heart, the second law is surprisingly simple. It states that in an isolated system, the overall level of disorder, or entropy, will always tend to increase over time. Things fall apart. Order gives way to chaos. Energy spreads out, becoming more diffuse. Think of an egg. In its whole state, its molecules are arranged in a very specific, highly ordered way. This is a low entropy state. Now, scramble that egg. The molecules are in a jumbled, chaotic mess. There are an astronomical number of ways you could rearrange those molecules and still have what looks like a scrambled egg. This is a high entropy state. The second law tells us that the universe will always move from the egg to the omelet, simply because there are vastly more ways to be disordered than to be ordered. This one-way street from order to chaos is what gives time its direction. It is the arrow of time. The reason you can't remember the future is because the future is the high entropy state that the universe is moving towards. The reason you remember the past is because it was a special, low entropy state. The great mystery is not that entropy is increasing, but that it was ever low to begin with, at the Big Bang. For a long time, life was seen as a puzzle. Life, after all, creates incredible order. From a chaotic soup of chemicals, life built intricate structures like DNA, cells, and complex organisms. We are islands of astonishing order in a universe that is supposed to be falling into chaos. So, does life defy the second law? The answer is a beautiful and resounding no. Life doesn't defy entropy. It is a magnificent vehicle for creating it. The second law applies to isolated systems, but Earth is not one. We are constantly bathed in a flood of low-entropy energy from the sun. A plant, through photosynthesis, captures this high-quality sunlight and uses it to build complex, ordered structures like sugars. This is a local decrease in entropy. But to achieve this, the plant releases a vast amount of low-quality, disordered energy back into the universe as heat. The total entropy of the universe goes up, exactly as the law demands. Think of a whirlpool in a draining bathtub. The whirlpool is a temporary, highly ordered structure. But it can only exist because water is flowing through it, moving from a state of higher energy to a state of lower energy. The ordered structure of the whirlpool is a consequence of the water taking an efficient path to a more disordered state. Life is that whirlpool. We are temporary, ordered structures that persist by channeling the flow of energy from a concentrated source, the sun, towards a state of greater chaos. Every breath you take, every thought you have, is part of this cosmic process of increasing the universe's total disorder. This flips the entire script. We are not a fluke. From a thermodynamic perspective, the emergence of life might even be a natural outcome. Life is an incredibly effective strategy for dissipating energy and increasing entropy. The universe's fundamental tendency towards chaos is not a bug. It is the feature that makes everything we care about possible. A perfect universe, one already at maximum entropy, is a universe where no work can be done. It is a universe where the whirlpool cannot form, because the water is already perfectly still. The creative power of chaos. If the universe's march toward chaos makes life possible, it stands to reason that its most creative processes are not gentle, but violent, chaotic, and destructive. When we look at the universe, from the birth of stars to the evolution of life, that is exactly what we find. Progress is born from the ashes of destruction. Let's begin with the stars. Every atom in your body heavier than hydrogen was forged in the heart of a dying star. It starts in the core of a star like our Sun, which spends billions of years in a state of relative equilibrium, fusing hydrogen into helium. But eventually, the hydrogen fuel runs out. This is where the creative chaos begins. Gravity causes the core to collapse and heat up, igniting the fusion of helium into carbon. For stars much more massive than our Sun, this cycle of collapse and chaotic ignition continues, creating heavier and heavier elements until it reaches iron. Fusing iron consumes energy instead of releasing it. The star's engine dies. What happens next is a core collapse supernova. The outer layers crash down, rebound off the core, and create a cataclysmic shockwave that blows the star apart in an explosion that can outshine a galaxy. This explosion is pure chaos. But in that second of furious burning, a process called explosive nucleosynthesis forges the majority of elements heavier than iron: gold, silver, platinum, uranium. The star has to die, scattering its elements across the galaxy, so that new things can be born. Those elements enrich interstellar clouds, which then form new stars and, for the first time, rocky planets. Without the chaos of a supernova, there would be no heavy elements to make those planets interesting. Our existence is owed to the universe's capacity for spectacular, creative self-destruction. This pattern of progress through chaos is mirrored in the evolution of life. Evolution is not a smooth, directed march. It is a messy, haphazard process driven by random chance. The source of all novelty in biology is mutation, random errors in the copying of DNA. The vast majority are neutral or harmful, introducing a form of disorder. But every now and then, a random mutation confers a small advantage. Natural selection then acts as a filter on this chaos, favoring organisms that are slightly better adapted to survive and reproduce. It is not a directed process. There is no grand plan. It is a walk through the space of possibilities, driven by randomness. The extinction of the dinosaurs, likely caused by a cataclysmic asteroid impact, was a tragedy for them, but it cleared the way for the rise of mammals and eventually, us. The history of life is punctuated by these destructive resets, which open up new niches for chaotic innovation to fill. Even in our own lives, we see this principle. True learning often involves confronting confusion, letting our old models of the world break down. It is in the moment of chaos, of not knowing, that a new, more complex understanding can emerge. Creativity works the same way. The process often involves making a mess, trying things that do not work, and generating dozens of chaotic, half-formed thoughts before a piece of order emerges. The universe does not build on perfection. It builds on ruins. This decay is not a threat to progress, it is the engine of progress. We started with a vision of a perfect universe and found not a paradise, but a silent, static prison where nothing could ever happen. The great irony is that the very things we might fear, decay, chaos, and an end, are the source of much of what we value. The universe is not a static object, it is a dynamic process. It is the story of energy flowing from order to disorder, a story made possible by the second law of thermodynamics. This flow gives time its arrow, painting the canvas of cosmic history. It powers the stars, whose chaotic deaths seed the universe with the building blocks of planets and people. It drives the random mutations and messy struggles of evolution. And it gives our own, fleeting lives a quiet significance. The fact that we are temporary, that our moment of ordered consciousness is a brief flicker, is precisely what makes our existence precious. Our struggle to create small pockets of order, a family, a work of art, a moment of understanding, is not a futile fight against the universe. It is the universe's own creative process, happening through us. We are the whirlpools, the temporary, beautiful patterns formed by the cosmic flow. A perfect universe would be a story with no final page, and therefore, no story at all. Our fragility, our constant, quiet effort against the encroaching chaos, is what gives our choices weight. It is what makes beauty breathtaking. So the next time you watch a log burn to ash, or feel the quiet ache of time passing, perhaps do not see it as a flaw in the system. See it for what it is, the glorious, messy, creative engine of reality. The universe isn't perfect, and that is, perhaps, the most perfect thing about it.